So I was tidying up before the end of the semester, and look what I found. It's this old scale. And I was like, this really takes me back, right? I mean, it was what, like 30 lectures ago that we were using this thing to come up with interesting problems to solve. And then I remembered that some of the problems we came up with were strangely difficult, and we never really figured out why. So recall the partition problem. That's the one where I give you a collection of weights of my choice, some arbitrary collection, and I ask whether it's possible to take all of the weights that I provided and arrange them on the scale such that every weight has to be put on the scale and the scale ends up balanced. Now, we already know, because we talked about this way back in lecture 12, that we can frame this problem in terms of sets of integers. So I give you a set S of n positive integers, and your job is to come up with two sets L and R, which represent the things on the left-hand side and the things on the right-hand side of the scale, such that every weight appears in either of L or R, no weight appears in both of them, and the sum of the elements of L is equal to the sum of the elements of R. Now, we also know that there are cases where this might be impossible, where no sets L and R exist for a particular input set S, and in that case, you are allowed to bail out. You can say that there is no solution. And we tried to tackle this problem in lecture 12, and we were successful. We were able to come up with an algorithm that solved it. We used a recursive backtracking search procedure, which ran an exponential time in the worst case. And although we came up with a few heuristics that seemed to speed things up in some cases, ultimately the worst case running time of our approach was exponential. It seemed to be a sort of hard problem. And it turns out that even if we change this into a decision problem, which is where we're turning it into a yes or no question, instead of asking you to find me sets L and R, I'm just asking you yes or no. Is it true that sets L and R actually exist? Is there a valid partition or not? If your answer is true, I don't even need you to tell me the values of L and R. Even if we turn this into a decision problem with a yes or no answer, the problem seems to be very difficult, and we weren't able to come up with an algorithm better than exponential time to solve it. And I'll go ahead and spoil it now. I actually mentioned this in lecture 12, but it turns out that nobody else has either. So there is no known polynomial time algorithm. And of course, in this lecture, which I'm going to do this a lot, when I talk about polynomial time algorithms, I'm always talking about polynomial time in terms of the size of the input. And for our purposes, for this problem, the size of the input would be the number of elements of the set S. Nobody has been able to come up with a polynomial time algorithm in terms of the size of the input to solve this partition problem, even the decision problem version, the yes or no question. Okay, so that came up in lecture 12. Another problem that came up in lecture 12 that we have managed to revisit a couple of times since then is the subset sum problem, which is where I give you a collection of weights, again, some arbitrary collection, as well as some goal sum W. And I ask whether there is a subset of the weights that I provided that you could put on the right-hand side of the scale such that the scale is balanced. In other words, is there a subset of this collection of weights that adds to W? And of course, we can frame this in terms of sets of integers as well. As much fun as it is to work with the antique scale, it turns out that it's just a visual device. And I can frame it in this case as a decision problem, a yes or no question. And we actually spent a lot of time talking about subset sum, and in fact, the subset sum decision problem back when we were covering dynamic programming. I think that was somewhere around lecture 32. Okay, so subset sum is where I give you a set S of n positive integers and one extra value, a goal sum W, and I just want you to answer the yes or no question. Is there a subset B of S such that the elements of B add up to W? Yes or no? Even if one exists, you don't have to give me one, just tell me whether one exists. But even this decision problem seems to be very difficult. So we weren't able to solve it in polynomial time, either of the times we tried to, but it turns out nobody else has been able to do that either. I guess you could say we came close to that when we were talking about dynamic programming. So using a dynamic programming technique, we were able to design this algorithm that can solve the subset sum problem in this amount of time, big theta of n times W. Now, this certainly looks like some kind of polynomial function, but it's not what we would call a polynomial time algorithm because it's not polynomial in the input size. It does involve the input size, so n is part of the input size. This is as good a time as any to observe something about the way that input sizes work. So really the input size for this problem, I guess the input consists of n plus 1 integer values. There's a thing that's going to come up a few times later in this lecture where I observe that actually the input size isn't really strictly just n plus 1. It might be better to say something like the input size is big O of n plus 1. There is some other constant factor buried in there, or there's some shenanigans going on because, of course, when we talk about the input containing n plus 1 integer values, there might also be the question of, how much space does it take to represent those integer values. I'm going to talk today about things that verge on the subject of computational complexity. When you go on to take a computational complexity course, you will realize that things like how many bits I use to encode integers is sort of a big deal when we're talking about certain complexity things. But fortunately for our purposes, from the point of view of an algorithms course, we don't have to worry so much about that. So for our purposes, it is worth observing, though, that the size of the input here is actually n plus 1. But we know because of the way that asymptotics work that actually we can treat the input we can treat the variable n as sort of being a proxy for the input size, because that plus 1 doesn't really make much of a difference in the grand scheme of things. Okay, so we had this algorithm that we designed using a dynamic programming technique that could solve the subset sum problem in n times w time. And of course, that does depend to some extent on the size of the input. The problem is that the value w isn't the size of the input, it's just part of the input. It's one of the input values. It's an input parameter. And so that means n times w is not polynomial time in the input size. It could be, if we're lucky enough to have a value of w that is proportional to some polynomial of the input size, but that may not happen in general. So of course the classic example of a case where that might not happen is, hey, what if w is equal to 2 to the n, or if it's larger than that? Well, in that case, if we sub in w in our expression for the running time is n times 2 to the n, which is very clearly not polynomial in the input size. Okay, so the subset sum problem therefore turned out to be pretty difficult as well. And I guess the question we ought to try to address, and I say address because it turns out that I can't really answer the question in a satisfying way, even in this entire lecture. The question that we ought to address before we're done with this course is what makes these problems so difficult? So in lecture 12, and a few times before that, we dragged out the antique scale and tried to develop various balancing problems. We found that some of them were easy. The very first one we solved, I think that was back in lecture 4 or something, was basically the binary search algorithm, which runs in logarithmic time. And yet, when we describe this partition problem or the subset sum problem, they seem to be strangely difficult. And what's sort of frustrating about this is not only that they seem to be strangely difficult, but we don't really have any certainty as to why they are difficult or even if they are difficult in the grand scheme of things. Just because we can't design a polynomial time algorithm doesn't mean that one doesn't exist. And just because it happens to be the case that nobody else has been able to design a polynomial time algorithm, at least as of the date of this recording in August 2025, that doesn't necessarily mean that a polynomial time algorithm doesn't exist either. It would be sort of satisfying, at least, if somebody could prove that this problem can only be solved in exponential time or slower. But nobody's done that. Nobody's found a polynomial time algorithm, and nobody's been able to prove that one doesn't exist. So the best that I can hope to do as far as addressing this question of what makes these problems so difficult is to point out that they actually have some hidden depths. So it's true that if we look at the partition problem or we look at the subset sum problem, they don't seem that complicated. Compared to other problems that we've solved since then, so I'm thinking, for example, of the maximum flow problem or the minimum cost maximum flow problem, which it turns out both of those problems actually can be solved in polynomial time. We didn't directly cover a polynomial time algorithm for minimum cost maximum flows, but one does exist. So those problems can be solved in polynomial time, and for my money, it does seem as if minimum cost maximum flows are pretty complicated compared to partitions and subset sum. So why are they so complicated? why are these problems here so difficult? What makes them, what gives them that extra complexity? And the best I can hope to do as far as explaining or addressing that question is to point out that actually these problems are more complicated than they seem. They have some hidden depths. And if we were to come up with a fast algorithm to solve them, it would actually, I guess you could say, begin the process of knocking down a whole bunch of dominoes in terms of other very difficult, very obviously difficult problems becoming easy to solve. Okay, so to begin to address this, I think the first thing we should do is maybe take a bit of a victory lap. We're talking here about problems that appear to be difficult. Why don't we go over some other problems that we've solved recently and observe other problems we've seen that don't seem to be difficult but look on their surface to be a little bit more complicated. Okay, so we'll start with this one. We've actually solved all sorts of interesting problems in this course, but I guess my mind is drawn to this one as a first step on our victory lap because the minimum weight spanning tree problem, in my mind, does have some similarities to subset sum. Now, it's not the same problem, certainly. It turns out, of course, that we can solve minimum weight spanning tree in polynomial time. But choosing a minimum weight spanning tree, doesn't that involve choosing a subset of something, in this case a subset of the edges of a graph, such that the sum of the subset that I choose has a particular property? It is the minimum possible sum among all spanning trees. Okay, so it has some similarities to the subset sum problem. Okay, so given an edge-weighted undirected graph G, compute a minimum weight spanning tree of G. And of course, we know that we can do this in polynomial time. This expression here, which happens to be the running time of a certain implementation of Boruvka's algorithm, Jarnik's algorithm, or Kruskal's algorithm, as we saw back in, I think, lecture 31, this expression is in fact polynomial in the input size. The input size in this case really is proportional mostly to the number of vertices, because the number of edges, which also is significant, which also is a factor in the input size, the number of edges is bounded above by v squared. So because we know about this relationship here, that the number of edges is big O of v squared, really the number of vertices is sort of a good proxy for the input size writ large in terms of talking about polynomial time algorithms. And so obviously since log of v is big O of v, this expression is polynomial in the number of vertices of the graph and therefore polynomial in the input size. So we can definitely solve the minimum weight spanning tree problem in polynomial time. And I should also observe, because we're going to spend a lot of time talking about decision problems in this lecture, that the minimum weight spanning tree problem that we solved in lecture 31 wasn't a decision problem. It was actually go and find me a tree, not just answer some question about the tree. So we could argue, I guess, that a problem like finding a tree and providing it does seem to be a little bit more difficult, at least in some semantic sense, than giving a yes or no answer. How about this problem? We haven't actually studied this problem at all. Compute a maximum weight spanning tree of a particular edge-weighted undirected graph. It actually turns out that although we haven't studied this problem, there is a very easy way of transforming the maximum weight spanning tree problem into the minimum weight spanning tree problem, which means if we can solve the minimum weight spanning tree problem in polynomial time, we can solve this one too. And the idea is basically the goal of the minimum weight spanning tree problem is to find the smallest possible sum of edge weights such that the edges that you've selected comprise a spanning tree. The maximum weight spanning tree problem is to do something very similar, which is again an optimization problem, but here it is to maximize that sum. What I realized, though, is that what I could do is just swap maximization for minimization. I could transform this graph into something whose minimum weight spanning tree corresponds to a maximum weight spanning tree of what I started with. So suppose that the graph I start with is called G. And what I can do is convert my graph G to a new graph that I could find a minimum weight spanning tree of by just negating the edge weight of every edge. So I'll just change 5 to -5, I'll change 3 to -3, and I'll change 10 to -10. And you can observe that really what I'm doing is making it so that a maximum weight spanning tree of my graph G would correspond to a minimum weight spanning tree of my new graph G prime. Also observe that creating G prime is pretty easy. I just make a copy of G, which I can obviously do in polynomial time, and then I iterate through all of the edges and I negate their edge weight. Again, that's pretty easy to do in polynomial time. So I have this graph now where I've got all of my edges have negative edge weights in this case, and observe that if I were to try and run run a minimum weight spanning tree algorithm on this graph, so suppose I use Kruskal's algorithm, the first edge I would take, for example, would be this edge here. And I'm not going to go through the entire example, but we can actually show that, in fact, a minimum weight spanning tree of G prime does indeed correspond to a maximum weight spanning tree of G. And moreover, the algorithms that I'm used to using for minimum weight spanning trees work just fine, even if my edge weights are negative. So that is one added thing that we'd have to demonstrate. We can't just convert between problems and assume that our conversion always works unless we prove that the converted instance actually has the property we're looking for, that is, that a minimum weight spanning tree of G prime does indeed correspond to a maximum weight spanning tree of G, but also that the algorithms that we're used to using would still work. We know that negative edge weights can sometimes cause us trouble, not for the minimum weight spanning tree problem, but for other problems. It turns out that in the case of minimum weight spanning tree algorithms like Barufka's algorithm, Jarnik's algorithm, or Kruskal's algorithm, for all of those algorithms, the proof of correctness depends on the cut property, or at least that's how we justified it in this course. And the cut property doesn't care at all about the sign of the edge weights. And so the cut property still holds even in the presence of negative edge weights, and therefore all three of these algorithms are still correct, even if edge weights are negative. And that means that I actually have a solution to the maximum weight spanning tree problem in polynomial time. Just convert it in polynomial time to an instance of the minimum weight spanning tree problem and use one of the algorithms that we already know to solve it. And the slides are observing, of course, that the conversion can be done in polynomial time. All right, well, moving on in our victory lap here, let's talk about minimum cost path. So given some edge-weighted directed graph that has no negative cost cycles, because we know that those cause trouble for the algorithms that we like to use, and I give you two vertices, a start vertex and an end vertex, find the minimum cost path from U to V. Well, of course, we know we can accomplish this in polynomial time. For example, I guess the safest choice is to use the Bellman-Ford algorithm because there may be negative costs on edges. And in this graph, in fact, there are. But I can definitely solve it in polynomial time because the Bellman-Ford algorithm has this running time here in the worst case. And of course, this is also definitely polynomial in the input size. It is at worst v cubed. Okay, so I can solve this problem in polynomial time. Okay, well, fair enough. Let's flip that around and ask instead for the maximum cost path. I showed a minute ago that if we can solve the minimum weight spanning tree problem, then we can also solve the maximum weight spanning tree problem. And I guess intuitively it does make some sense that if the minimization version of a problem can be solved in polynomial time, so can the maximization problem, right? Okay, so given some edge-weighted directed graph with no negative cost cycles, find the maximum cost path from a particular start vertex to a particular end vertex. Such a thing does exist. So here's an example of a maximum cost path from vertex A to vertex F. You can go ahead and try and verify that if you want. Good luck, because what we're about to see is that it turns out computing these things can be rather difficult. Unlike the maximum weight spanning tree problem, where we could just flip it around and turn it into an instance of the minimum weight spanning tree problem, there actually is no straightforward way to adapt the maximum cost path problem such that I can actually use polynomial time algorithms for minimum cost paths. It actually is still true, if I negate every edge weight, that the minimum cost path from A to F will in fact be equivalent to the maximum cost path in the original graph. The problem is the algorithms that I'm used to using for minimum cost paths won't work in this case. And there's a pretty obvious reason. So in general, if I flip all of my edge weights from positive to negative to turn the maximization problem into a minimization problem, in a general graph, there could be directed cycles. And if there are any directed cycles, then I'm going to end up with negative cost cycles. And therefore, none of the algorithms that I'm used to using, like the Bellman-Ford algorithm, will work correctly. Now that by itself doesn't mean the problem is intractable. It doesn't mean the problem can't be solved. It just means that if we want to solve the maximum cost path problem, we're going to have to develop some other algorithm. And unfortunately, bad news, it turns out that nobody has been able to find a polynomial time algorithm for the maximum cost path problem, even though we know of several polynomial time algorithms for the minimum cost path problem. Hopefully you can detect that I'm having to walk a very fine line here. I keep catching myself before I say something like, there is no polynomial time algorithm. I mean, it's true that at the moment, there is no polynomial time algorithm. I have to be very careful to keep saying that no polynomial time algorithm is known, because I have no way of justifying that there isn't one. It certainly feels like if one exists, it must be pretty complicated or obscure, because, for example, the algorithms that we know and love for minimum cost paths were invented about 70 years ago or so in the mid-1950s. And in the intervening 70 years, this discipline has sort of exploded in all directions, and I imagine a lot of work has gone into trying to solve the maximum cost path problem. There are a lot of reasons why this is actually quite an important problem that we're not going to get into here, but you'll see again in some computational complexity course later. If you want something to look up the traveling salesperson problem, or look up Hamilton cycles, or Hamiltonian cycles. And so a lot of work probably went into trying to solve the maximum cost path problem, and the fact that it's been 70 years and nobody's found a fast algorithm certainly implies that if an algorithm exists, it must be hiding somewhere, pretty well. I mean, it must be pretty obscure of an algorithm. I don't know if that means we should give up hope. Certainly such an algorithm could exist, but it does sort of hint that the problem may indeed be rather difficult. While we're on the subject, is there a way that we could turn this into a decision problem? So earlier, I guess as a point of contrast, we argued that, well, maybe finding a partition or finding a valid subset is difficult, but what about just asking the question about whether a partition or a particular subset exists? And we found that in those cases, apparently the problem is still difficult for both partition and subset sum. Can we turn maximum cost path, which is obviously an optimization problem where the result is a path in a graph, can we turn that into a question that has a yes or no answer? And it turns out we can. And it actually turns out that there's a common thread, a common technique that we can use to turn any optimization problem into a decision problem. And the idea is what we do is add one extra parameter to the input, a bound, and then the yes or no question becomes not give me the path, but just tell me whether or not a path exists that is at least as good as the bound. So with a maximum cost path, we want paths that have as large of a cost as possible. So what I'm going to do is add a bound k to my input, and the decision problem version becomes, the answer will be true if there exists a path with cost at least k. And then false if no such path exists. In general, we can use this technique for a lot of optimization problems, and we're going to do that a lot later in this lecture. We just add some parameter that bounds the optimal solution, and then use that as a way of turning it into a yes or no question. And we can observe that this does give us some way, if we wanted to, of solving the optimization question. So if I wanted to ask the question, what is the maximum cost? I could just keep using the decision problem over and over again with different values of k to narrow down what the maximum cost actually was. And so what I've done is added a parameter k such that the k serves as a bound on the optimal solution, so I can just ask the question, is the optimal solution at least as good as k? It's also worth observing that if I were to have a fast algorithm to actually find maximum cost paths, then this would be pretty easy. If I wanted to solve the decision problem and I had an algorithm to actually find a path, I could just find the maximum cost path and then use the cost of that path to answer this question, very simply. So clearly, the optimization version of the problem is at least as difficult as the decision version. You could argue the decision problem must be, in a sense, easier than the optimization version. Now, conversely, if there is a fast algorithm to solve just this yes or no question, just the decision problem version, I could use that over and over again with different values of k to work out the actual maximum cost. And I could do something similar to what we did back when we talked about dynamic programming, for example, to develop that algorithm for subset sum, to in a sense work backwards to actually find the path itself using the decision problem repeatedly. Okay, so really what I'm trying to argue here is that we can take all of these problems that appear to be hard and boil them down to decision problems as a way of sort of enforcing consistency. So if I want to talk about a bunch of different hard problems, I can turn all of them into decision problems so that I can, in a sense, compare them to each other. But it turns out that even if I turn this into a decision problem, no polynomial time algorithm is known. So there's no polynomial time algorithm that even tells me whether a path of a particular cost exists if the cost is lower bounded. Now, if I change this into an upper bound, so if I say the cost is at most k, well, then, of course, what I'm actually doing is solving the minimum cost path decision problem, and we can do that in polynomial time. This is quite a puzzler. So the minimization version of the problem can be done quickly, but the maximization version of the same problem seems to be difficult. We can't seem to prove it just yet, but it seems to be difficult. There's some huge jump in difficulty by switching from minimization to maximization, a jump that we didn't see with other relatively similar optimization problems like minimum weight spanning tree versus maximum weight spanning tree. Okay, moving on to graph theoretic properties. So these are things where we haven't directly covered algorithms for the general case, but this is a particular problem we're going to talk about a lot later in this lecture. We've seen this before. A couple of lectures ago, this came up in the context of flow networks, but a vertex cover of an undirected graph is some subset of the vertices, we'll call it C, such that every single edge of the graph has at least one of its endpoints in the set C. So the blue vertices shaded here comprise a vertex cover. Observe that if I pick any edge, at least one of its endpoints, in this case actually both of its endpoints, at least one of the endpoints of each edge is in the vertex cover. So that's what makes it a vertex cover. If there were an edge where both endpoints were uncovered, I wouldn't be looking at a vertex cover. We observed back when we saw this for the first time that it's very easy to make a large vertex cover. So if I just take every vertex in the graph, that will always comprise a vertex cover. It seems to be difficult to make a vertex cover which is small, and so the natural optimization problem is to compute a minimum vertex cover, which obviously is a vertex cover of minimum size. On this graph, a minimum vertex cover happens to have size 8. Now there actually are a few different ones, but one of them is shown here. One point I'll make that I'm going to come back to later is that observe that if a graph has a vertex cover of size 8, it's very easy to make a vertex cover of size 9 or of size 10 or of size 11 or whatever. If I want a vertex cover of size 9, just take a vertex cover of size 8 and add an extra vertex. Adding an extra vertex doesn't break anything. The extra vertex is sort of redundant, but I can always make a larger vertex cover given a smaller one. Now, we actually know already that a minimum vertex cover of a bipartite graph can be computed in polynomial time. And if you want to know why, I guess go back 2 lectures and look at that. So if we have a bipartite graph, we can compute a maximum matching or a minimum vertex cover using a maximum flow algorithm by transforming the bipartite graph into a flow network using the flow network construction that we already discussed. And back in lecture, I guess that was lecture 38, I mentioned this. It's sort of weird that finding maximum matchings for general graphs is still polynomial time. There is actually a polynomial time algorithm that we didn't cover, but one does exist, to find maximum matchings of general graphs in polynomial time. And yet, for some reason, a minimum vertex cover of a general graph cannot be found in polynomial time that we know of. So no polynomial time algorithm is known to compute minimum vertex covers or of arbitrary graphs that aren't, for example, bipartite graphs, or even to solve this decision problem here. So here I've phrased the vertex cover optimization problem as a decision problem in the way that I mentioned earlier. I add a bound k, and the question becomes, the yes or no question is there a vertex cover of G whose size is at most k? And even this yes or no question does not have a polynomial time algorithm that we know of. It seems to be a difficult problem. Okay, a related graph theoretic thing that we haven't discussed at all before, and we'll never discuss again, sadly, even though I sort of like this problem, is something called a dominating set. And I'm bringing this up here mostly just to add some flavor, to add some breadth to the set of problems that we are discussing. A dominating set of an undirected graph is, again, a subset of the vertices. We're going to call it D. In this case, it has the property that if I look at any vertex in the graph, either that vertex is in the set or it's one of its neighbors is in the set. So let's pick a vertex in this graph. Okay, there's a vertex. Well, this vertex is obviously in the set D. So it's shaded blue, so it's in the set D. Let's pick some other vertex. Here we are. This vertex is not in the set D, but one of its neighbors is in the set D. So we can frame that formally by saying, if I look at any vertex U, either U is in the set, or there is an edge from U to some vertex V, such that V is in the set. And so we can also think of this in terms of, if I look at every vertex in the set, and I just color in each of its neighbors, then I should end up with every vertex in the graph being covered, or being dominated, to use the term, that's where you get the term dominating set from. Okay, so a dominating set is a set such that every vertex of the graph is either in the set or one of its neighbors is in the set. We can also, although I like this way of writing it because I feel like the words sort of make it less notationally dense, we can also define a dominating set with this much more cryptic looking notation where we use the closed neighborhood of a vertex. So a set D is a dominating set if and only if, for every single vertex V, the closed neighborhood of V intersect D is non-empty. There's at least one vertex in the intersection of the closed neighborhood of V and the dominating set. Now, dominating sets, again, are just like vertex covers, and maybe you can see the similarities. They are sort of relatives of each other. Dominating sets, it's very easy to make a large one. I mean, I could just include every vertex in the graph in my dominating set, and that would always give me a dominating set. And so that means the natural optimization problem is making one that is small. So a minimum dominating set is a dominating set of minimum size. On this graph, as you can see, a minimum dominating set has size 3. Also, you can observe that there clearly is more than one minimum dominating set because I could just flip the dominating set that I have vertically, and I could choose, let's say, this vertex, and this vertex. So minimum dominating sets aren't necessarily unique. And similar to vertex cover, unfortunately, I guess you saw this coming, it turns out that no polynomial time algorithm is known to find a minimum dominating set, or to solve the decision problem of whether a dominating set of a particular size exists. And I know this one for sure because earlier in my career, I spent a whole ton of time studying the dominating set problem. Okay, moving on. Recall, I think this is coming from lecture 27, that a two-coloring of an undirected graph is a way of coloring the vertices of the graph with two different colors, let's say we use red and blue, such that no two adjacent vertices have the same color. Now, we've actually seen two colorings before. We've actually seen them all the time. It's just that usually we call them bipartitions. So we know from lecture 27 that a two coloring is equivalent to a bipartition. Usually when we talk about bipartite graphs, for example, 2 lectures ago, we draw them in that traditional bipartite graph representation where the two sides of the bipartition are drawn on the left and right, and all of the edges go between them. But we can also think of a bipartite graph as a graph that is two-colorable, or a graph for which there exists a two-coloring. And fortunately, after this long list of apparently difficult problems, we finally happened upon a problem that can be solved relatively efficiently. So we know from lecture 27 that because a two-coloring is equivalent to a bipartition, and since a basic traversal algorithm like BFS or DFS can find a bipartition, we can in fact compute two colorings in polynomial time. In fact, we can do it in linear time by performing one traversal. So fortunately, we finally have a decision problem on our hands with a polynomial time algorithm. So the problem is called two-coloring. I give you an undirected graph, and I just ask you a yes or no question. Is there a two-coloring? That is to say, is the graph bipartite or not? And we can solve that in polynomial time. Okay, fair enough. What about graphs without a two-coloring? So here is a graph that is not bipartite and therefore has no two-coloring. One way we know that it's not bipartite is that it contains a cycle of odd length. If you want to know more about that property, go back and look at lecture 27. This graph is not bipartite because it contains an odd length cycle and no two coloring exists. Okay, well that's too bad. But it turns out I actually can produce a three coloring. Here it is. So because I can show you a three coloring, clearly the graph is three colorable. Now there are graphs out there that aren't even three colorable, but maybe they're four colorable or five colorable or something. We can see, I guess, that there's ways of coloring vertices with more than two colors. So this graph does have a three coloring. So we could ask the question, hey, how could I go about computing a three coloring? It turns out that no polynomial time algorithm is known for the three-coloring decision problem. So I hand you a graph and I say, is there a three-coloring of this graph or not? Even answering that question, whether you can find me a three-coloring or not, just giving me an answer to this question is something that we can't seem to do in polynomial time. This is also sort of unsettling. Just like the situation with minimum cost path and maximum cost path, it's really weird that we're seeing such a massive jump in difficulty. So two coloring, if I'm allowed to use two colors, that can be done in linear time. It can be done definitely in polynomial time. If I just add one more color, the problem becomes incredibly difficult. It doesn't seem to be, as far as we know right now, possible to do it in polynomial time. Now, of course, with only those two reference points, you could think, well, wait a minute, maybe it's just that every color you add significantly increases the difficulty of the problem, right? So 2 coloring is easy, 3 coloring apparently is hard, and 4 coloring is even harder. But what's even more bizarre is that it turns out that 4 coloring doesn't seem to be any more difficult than 3 coloring. The only real jump in difficulty is between 2 coloring and 3 coloring. 4 coloring is a little bit more difficult, but there isn't the same huge jump in difficulty. The algorithms that exist for 3 coloring and the algorithms that exist for 4 coloring run in about the same amount of time, give or take a few polynomial factors. Okay, and then finally, to wrap things up, I want to talk about a set of problems that we've never seen before. These are very fundamental problems. I don't think that they're going to be too surprising. They don't require knowledge of graphs or anything else more complicated. They require basic knowledge of Boolean algebra or logic formulas, which we all have. So consider a Boolean formula, let's call it Z, on n different Boolean variables. So we'll call them x1 through xn. In this section, I'm going to use our familiar logical operators. I'm going to use the symbolic ones, not the ones we use in programming languages, where this little V-shaped thing is logical OR. And we have seen these before. We saw these when we talked about dynamic programming. And this sort of, I guess it's a wedge-shaped thing. I know that because that's the LaTeX command for it. This would be logical AND. And also, when I want to talk about the logical NOT operator, I'm going to write it like this. So you could read this as being not x1, so the logical inverse of x1. When we talk about these Boolean formulas, it's sort of nice to be able to talk about the number of times variables appear in the formula. And to do this, what I want is some convenient way of being able to refer to each of these things by one consistent term. And most of them, like this one and this one and this one and this one, are just variables that appear, but this one here is a variable that got negated. It's just a single variable, and I'm looking at its negation, so not x1. And so what I'm going to do is call these things literals. So a literal is an appearance of a single variable xi or the expression not xi. So either of those is a literal. So to be clear, this expression contains 5 literals. Now this not operator is a not operator outside of a full expression. So this not operator does not correspond to a literal. A literal is one variable either directly or the negation of that variable. Here's a question. So I give you a Boolean formula on n variables, and I ask the question, is there any way of assigning truth values to my variables? So an example of an assignment of truth values, how about is x1 is true, x2 is false, x3 is true. Okay, and I guess x1 is true, x2 is false. Is there any assignment of true-false values such that the entire formula comes out to be true? The term that we typically use for such an assignment is a satisfying assignment. Is it possible to assign values to our variables such that the entire formula is satisfied? For this formula, it turns out that the answer is yes. If I set, was that the one I chose? Oh, look at that. Okay, if I set x1 to be true, x2 to be false, and x3 to be true, it turns out that the entire formula works out to be true. And so this assignment here is an example of a satisfying assignment for the Boolean formula. I hope it's clear because we've all used Boolean expressions in programming languages before. They are a sort of fundamental thing. Hopefully it's clear that evaluating a Boolean formula is pretty simple. If I give you a collection of truth values, it's very easy to work out the value of a Boolean formula. Certainly easier than doing things like finding minimum weight spanning trees. And so the question is, can I answer the question of whether a satisfying assignment exists quickly? And unfortunately, apparently, no, I can't. No polynomial time algorithm is known for the corresponding decision problem. So the decision problem is traditionally called satisfiability. So I give you a formula and I ask you, is this formula satisfiable? Now the formula itself, so I give you a formula Z, let's say it contains m literals over n variables. Now it's tempting to think that this number of variables is a proxy for the input size, but that's not quite true, because I could have n variables and each variable could show up billions of times for all I know. If I count the number of literals, that's a better way of measuring the size of the input, the actual size of the formula. And so a polynomial time algorithm in this case would be one that's polynomial in M, not necessarily one that's polynomial in N. So the satisfiability decision problem is I give you some arbitrary Boolean formula on n variables, and I just want a yes or no answer. Is there some way to satisfy this formula? I don't even need you to give me the satisfying assignment. Just tell me whether one exists. No polynomial time algorithm is known for that problem. While we're on the subject, it's worth noting that we can view, if we think of digital logic circuits, we can view those as similar to Boolean formulas. Arguably, you can convert back and forth pretty easily. So I can take any Boolean formula and I can write it out as a digital logic circuit. Speaking of which, if you don't know what digital logic circuits are, just go ahead and cover your ears for 5 minutes. It's no big deal. We don't really need them later in the lecture, but it's worth bringing them up at this point. So I can take any digital logic circuit and convert it into a Boolean formula. It turns out that this circuit corresponds to the formula we saw a couple of slides ago, and I can take any formula and implement it as a digital logic circuit. And so just while we're on the subject, I should observe that we could therefore frame our satisfiability problem in terms of digital logic circuits. And it should be no surprise, therefore, that no polynomial time algorithm is known for that problem either. So we don't know any polynomial time algorithm that takes a digital logic circuit on M logic gates and tells us whether or not there is any way to assign the inputs such that the circuit evaluates to true. It actually also turns out that even if I restrict the types of formulas that I'm allowed to use, the corresponding satisfiability problem doesn't seem to get very much easier. Okay, so I'll give an example of one restriction that we're going to use later in this lecture. To do that, I have to define a term. So a clause in a logical formula is defined to be a bunch of literals joined together by logical OR operations. And it must be logical OR operations, and they must be literals, not other sub-expressions. So this thing is a clause. It is a bunch of literals. In this case, there are 6 of them joined together by logical OR. Here are some examples of things that aren't clauses. So x1 and x2. No, that's not a clause because that involves logical and. That involves a conjunction. Another thing that is not a clause would be something more complicated like x1 or x2 and then a big not sign over that, or x3. So although I'm only using logical OR, because I'm applying a not operator to a sub-expression, this is not a clause. A clause is allowed to contain the not operator, but only on a single variable. So it's a bunch of literals and the logical OR operator. Okay, that's a clause, a disjunction of literals. Now, an entire Boolean formula is said to be in conjunctive normal form, or CNF for short, if it consists of a bunch of clauses joined together by the logical AND operator. This would be called a conjunction of clauses. And so conjunction refers to logical AND. So conjunctive normal form, or CNF, is clauses joined together by AND. If the clauses are joined together by the OR operation, well, actually, you're just making a bigger clause at that point, frankly. But for our purposes in a couple of slides, basically, whatever's outside the brackets has to be the logical AND operator and nothing else. And the clauses may not be negated. So this would not be allowed in conjunctive normal form. Even if I restrict my formulas to be in CNF, which I think if you stare at it, you'd agree, the CNF is much simpler. It's pretty restricted compared to arbitrary Boolean formulas, which can have any number of layers of depth and can be inverting in individual pieces. Here, I'm just doing a bunch of logical OR operations and then chaining these clauses together by AND. Even if I restrict my Boolean formulas to be in CNF, and we'll call the corresponding problem CNF satisfiability, even then, no polynomial time algorithm is known for the corresponding decision problem. There is no polynomial time solution to the yes or no question, well, at least that we know of, the yes or no question of whether a satisfying assignment exists. We can go further. What if we, instead of just restricting the way the formula looks, we restrict the size of each clause? So suppose, for example, I insist that every single clause contain exactly 2 literals. Okay, well, in that case, we can make some progress. Oh, actually, I should mention this before that. If you open a book on computational complexity, I will bet you that you see a definition of a satisfiability problem, I'd say pretty much in chapter 1. These things turn out to be very important. When you look at that definition, depending on the book that you open, the way that they define the generic satisfiability problem, what we have defined in the most general way possible, they might define it differently. So the stack of computational complexity books I have sitting next to me right now, in that stack of books, the different books define the basic satisfiability problem in a variety of different ways. It turns out that's no big deal because for the purposes of complexity results, as we are going to see in about, I don't know, like an hour or so, for the purposes of complexity results, they actually are of similar difficulty. But you may see in your future computational complexity course that the basic satisfiability problem is actually defined to be CNF satisfiability. They may not even bother addressing the more general case. Okay, so suppose that we take a CNF formula and we insist that every clause must contain exactly 2 literals. So here's an example of such a formula. We would say this formula is in 2 CNF because every clause has 2 literals. There can be as many clauses as we want, but each clause must contain 2 literals. It turns out that we can find satisfying assignments to this type of formula in polynomial time. We'll call this problem 2 satisfiability. If each clause contains 2 literals, then we can in fact answer this decision problem in polynomial time. The algorithm that we can use to do it is really interesting, and I wish we could cover it, but we don't have time to cover it. If you look it up, you'll observe that it is a great way to apply our knowledge of strong connectivity from back in, I guess that was lecture 29. So if I have a formula with 2 literals per clause, I can find a satisfying assignment in polynomial time. What if I want to add a 3rd literal to each clause? Well, in that case, the problem becomes strangely difficult. So again, a weird jump in difficulty, just like minimum cost path versus maximum cost path, or 2 coloring versus 3 coloring. If I'm allowed to have 3 literals per clause, no polynomial time algorithm is known. And just like with the coloring case, you could say, well, maybe that's because every extra literal you add amplifies the difficulty of the problem by a huge amount. But that doesn't seem to be true. It seems as if we go to 4 satisfiability, where there are 4 literals per clause, the problem doesn't seem to become that much harder than 3 satisfiability, which again sort of adds to the mystery and the sense of frustration about this. Why is there this huge jump in difficulty, and why can't we at least prove that the problem is hard? All I keep saying is no polynomial time algorithm is known. I don't know whether one exists, and I can't show that one doesn't exist. So, while most of the algorithms that we have studied in the course can be solved in polynomial time, we've already encountered quite a few problems that apparently can't, that as far as we know can't, and I just enumerated a few more that nobody can find polynomial time algorithms for. I should add, of course, that this list is not exhaustive in terms of what we've covered in this course. If I think about stuff like sorting, well, that can obviously be done in polynomial time. When I think about stuff like graph traversals, okay, well, that can obviously be done in polynomial time. When I think of things like searching problems, well, searching is a very general term, but we've seen a lot of searching problems that definitely can be done in polynomial time. We've spent a huge amount of time in this course not only learning about what it means to analyze algorithms and what a good algorithm or a fast algorithm is, but also identifying tons and tons of efficient algorithms that we can evaluate in polynomial time. I guess other ones we can think about are convex hulls. They can be computed in polynomial time. I can do Huffman coding in polynomial time. So we've seen lots of polynomial time stuff. However, we've also had a few run-ins with problems that, although they seem relatively simple, for some reason cannot be solved that we know of in polynomial time. So today we've seen, for example, that maximum cost paths don't seem to have a polynomial time algorithm. That's really spooky because minimum cost paths do. Computing minimum vertex covers apparently is also quite difficult. So is computing minimum dominating sets. Okay, well, fair enough. We haven't seen any other similar problems that are easy, so whatever. Although we have seen that minimum vertex covers can be computed quickly in some cases for bipartite graphs. We've also noticed that the maximum matching problem, for bipartite graphs, we compute that the same way we compute the minimum vertex cover, but in general graphs, maximum matchings can be computed in polynomial time, whereas for general graphs, apparently minimum vertex covers can't. Computing a minimum cut, well, we can do that with the Ford-Fulkerson algorithm or with the Edmonds-Karp algorithm in polynomial time. It turns out, although we haven't talked about this today, that computing a maximum cut is very difficult. That the only way we know of to do that is some exponential time search. That's also sort of weird. And then there are the cases of 2 coloring and 2 satisfiability, which can be done in polynomial time, whereas 3 coloring and 3 satisfiability apparently can't. And of course, the more general satisfiability problem can't either. And then that brings us back to subset sum and partition. Okay, so a case I tried to make earlier was that subset sum and partition don't feel that difficult. I say, here's a scale, here's a bunch of weights, a set of integers. Just answer a simple yes or no question. Can I balance the scale? And in what world could that be more difficult than computing a minimum cost, maximum flow? It just feels as if the problem can't be that hard. And yet it seems as if they are difficult. We can't find fast algorithms to solve them. And so I said earlier that all I can do in this lecture is to try and address the question of what makes these so hard, to try and expose some of the hidden depths. So the set of problems that we've seen that apparently aren't polynomial or maybe aren't polynomial, that these span all sorts of different applications. We have these very low-level sort of logical formula-based things. We have some graph-theoretic properties that are a bit abstract. We have practical optimization problems like maximum cost path, although actually these two are also practical optimization problems in certain cases. And we've got these abstract problems involving balancing the scale. And all of these seem to have this infuriating property that nobody can find a polynomial time algorithm, but also that it doesn't appear as if anybody can prove that no such algorithm exists. And even if we frame all of these things as decision problems, and by now hopefully it's clear that we can do that, we can just add a bound to the optimization problems and turn it into a decision problem, even if we do that, no polynomial time solution in terms of the input size is known. But it turns out that these problems aren't as different as they seem. There really are some hidden depths. And actually, I could make this list a lot longer. Now, I don't have an infinite amount of time to spend on this, but it turns out that there are thousands of problems that are in the same boat, where the problem itself is very easy to specify, and yet no polynomial time algorithm is known, but nobody can prove that no polynomial time algorithm exists either. So I could put thousands of different problems in this box, and the claim I'm going to make on the next slide would still hold, which is, if a polynomial time algorithm exists for even one of these problems, then it turns out that all of them can be solved in polynomial time. And so that's actually a huge deal. Like, that's what I'm going to do to address the question from the beginning. I can't show you a polynomial time algorithm because none is known. I can't prove that a polynomial time algorithm doesn't exist either because we have no way of knowing that at the moment either. However, what I will be able to demonstrate is that if you can find me a polynomial time solution for even one of these problems, I can give you a polynomial time solution to all of the other ones, despite the fact that the problems do seem quite different. Maximum cost path does seem to be worlds apart from subset sum. To demonstrate the similarities between them, I'm going to start with an easy case. So we already know that partition and subset sum have some similarities, and in fact, I am now going to go back over a proof that we did in full in Lecture 12. And that's one hint that the course must be nearing its end, because certainly it's a sign that I must be running out of material if we're getting into the reruns. So what I want to start with is I want to demonstrate that if there is a polynomial time algorithm for the subset sum problem, then I can solve the partition problem in polynomial time as well. So this entire proof actually is in Lecture 12. I copied and pasted the slides. Therefore, I'm going to go through it a bit more quickly here. I do feel like having the entire thing, like seeing it again, is useful because of the similarities between this proof and the ones that we're going to see later, which are a bit more of an acquired taste. Okay, so the input to the partition problem is a set S of integer weight values. And any solution to the partition problem must distribute every single one of the weights that was provided between the two sides of the scale. Okay, so as we recall from Lecture 12, what I could do is I could add up the total weight of all, I could just compute the sum of all of the weights that I was given. We'll call that value t. And what I observe is that if we have a way of finding a valid partition, really what we're doing is putting about exactly half of the weight on each side of the scale. Because if the scale is balanced, the same amount of weight is on both sides. And the only way that would work if I have a collection that adds up to t is if each side contains exactly t over 2 units of weight. And then I realized that if I can find some subset that adds to t over 2, then whatever I left behind, so suppose this subset b adds up to t over 2, whatever I left behind, so the remaining elements, s minus b, well, this has to add up to t over 2 as well. Because logically, if the whole thing adds to t, and I take t over 2 away, the remainder has to also add to t over 2. Okay, so what that's telling us is that if I can find some subset that adds to t over 2, the set b and s minus b, those two sets together, will form a valid partition. And so I have found a way of solving the partition problem if you can give me an algorithm for the subset sum problem. And moreover, to make the conversion, to actually use this transformation, all I really have to do is compute the value of t, I guess, and then divide it by 2. So it's very easy for me to take a set of weights that you give me for the partition problem and use it to construct an instance of subset sum in polynomial time. Okay, so a solution to the partition problem over a set S is equivalent to a solution to the subset sum problem over the pair S with the goal sum t over 2. And so the size of this subset sum instance, which is just the set S plus one extra value, is very clearly polynomial in the size of the partition instance. The only computation I had to do for the transformation was to compute the value of t, which obviously I could do in polynomial time. I could do that in linear time. I just iterate over the values in S and add them all together. And therefore, if you give me a polynomial time algorithm for subset sum, all I have to do to solve partition is convert my partition instance to a subset sum instance, and that would take polynomial time, and then run the polynomial time algorithm for subset sum. And so that would give me a polynomial time algorithm for partition. And what we just did, and what we did back in lecture 12, is an example of something called a reduction. I reduced the problem partition to the problem subset sum. Because the reduction that I performed only required polynomial time, we can now say that the partition problem is polynomial time reducible to subset sum, which tells us that if I have any algorithm for subset sum, I can solve partition. And in particular, any polynomial time algorithm for subset sum can solve partition after a polynomial number of pre-processing steps to turn my partition instance into a subset sum instance. What this is also telling us sort of intuitively is that the partition problem is no more difficult than subset sum. If I can use subset sum to solve partition, in a certain sense, subset sum is sort of harder, or at least equally as difficult as partition. And in a sense, we could think of it as being equally difficult because of this next result. So the next result is the opposite thing. It's saying that if there's a polynomial time algorithm for the partition problem, then the subset sum problem can be solved in polynomial time as well. This is going to be another reduction. This reduction is a little bit more involved. Okay, so you give me a subset sum instance SW, a set of weights S and a goal sum W. I'm going to construct a partition instance such that there is a subset of S with weight W if and only if my new partition instance has a valid partition. Okay, so as before, we're going to add up all the weights in S and call that value T. I'm going to make a new set of weights called S prime. This is going to be my partition instance. It is going to consist of the weights that you gave me, the set S, plus two extra new weights, a big weight called T and another big weight 2 times W. Observe that computing the set S prime is pretty easy. It can very clearly be done in polynomial time in terms of the size of S, because all I'm doing is iterating over it to compute T and then adding two extra things to it. Now note that the sum, if I add up everything in S prime, the sum works out to be 2 times T plus W, which means if there is a valid partition of S prime, it'll result in there being T plus W units of weight on each side of the scale. Okay, so what that's actually telling us, though, is that if I have t plus w units of weight on each side of the scale, then if I'm looking at a valid partition of this whole thing, there is no way that my two new weights would ever be on the same side. So because the weight of these two things together is t plus 2w, which is obviously greater than t plus w, there is no way that both of these weights can be on the same side of the scale, because that would make whatever side of the scale that was too heavy. What that's telling us, of course, is that the weight t has to be on one side and the weight 2w has to be on the other side. Okay, so suppose that I find some valid partition of this set S prime. That means that each side of the scale has t plus w units of weight. Actually, I'll write this underneath. So each side of the scale contains t plus w units of weight. Now, obviously, every weight has to be used, so this weight here has to appear on one side of the scale. Suppose, without loss of generality, that the weight t appears on the left-hand side of the scale. And we know that the weight 2w must therefore appear on the other side. So if I look at the remaining weights on this side, none of them are the weight 2w. Okay, so I've got the weight t over on this side, and the remaining weights on this side are some subset of my set S. And because I have this weight t, the remaining weights add up to weight w, which means that the remaining weights on whatever side of the scale contains the weight t will comprise a subset of the original set S that adds up to w. And so I found a way of solving finding a solution to my subset sum instance. Okay, so that means the set S prime has a valid partition if and only if the set S has a subset with total sum W. Since the size of S prime is very clearly polynomial in an asymptotic sense in the size of S, and since the computation of T and the construction of S prime is pretty easy and therefore requires polynomial time, so all I have to do is add two extra elements to a set as well as sum up the values in S, that means that subset sum is polynomial time reducible to partition. In a polynomial time number of steps, I can turn an instance of subset sum into an instance of partition, which means if you give me a polynomial time algorithm for partition, I will have a polynomial time algorithm for subset sum as well. Okay, we're ready for a definition. Now, what we're doing here is we're trying to tie up some loose ends in this algorithms course by being able to talk about the complexity of algorithm problems. Now, computational complexity is a very big deal, and you will take some course in the future where you cover computational complexity in greater detail, where definitions like this will be given in far greater detail than they are given here. The definitions given here are sufficient for the sake of polynomial time operations, so when we talk about polynomial time reductions, these are sufficient. However, in your future computational complexity course, you will see much more complicated definitions for reductions because there are other kinds of reductions you might want to do as well. Okay, so let's suppose that P1 and P2 are two different decision problems, problems with yes or no answers. A polynomial time reduction from P1 to P2, that is to say, a polynomial time reduction that turns an instance of P1 into an instance of P2, formally, that is an algorithm called R, which takes some input to P1 and turns it into some input to P2. And it's a polynomial time reduction if algorithm R requires polynomial time in terms of the size to our original input to P1. One interesting implication of this is if the reduction requires polynomial time, the size of what it produces, the instance to the second problem Q2, that actually has to be polynomial in the original input size. Because if algorithm R produces the input Q2 in polynomial time, well, clearly Q2 can't have exponential size, because how could a polynomial time algorithm create something that has exponential size? Okay, so algorithm R, the reduction, turns an instance of problem P1 into an instance of problem P2. And the condition that we require is that the resulting instance of P2, which we call Q2, evaluates to true if and only if the original input Q1 evaluates to true for problem P1. So we are mapping true to true, basically. Now, suppose that a polynomial time reduction exists from a problem P1 to a problem P2. Well, of course, then we can say that P1 is polynomial time reducible to P2. And we're going to denote that by this notation here. this sort of specialized less than or equal to sign with a little subscript p. So, and you can see that I've chosen this less than or equal to sign. Well, I say I've chosen this. This is standard notation. We're using a less than or equal to sign. That's a good way of connoting that what we're really saying here is that problem P1 has a difficulty which is at most the difficulty of P2. Because if I can use P2 to solve instances of P1, clearly P2 has at least the same amount of computational power as P1. Also note that we've used an operator that looks like the less than or equal to operator for a reason, and polynomial time reducibility behaves a lot like our familiar less than or equal to operator. For example, if I look at any problem P, any problem is considered to be reducible to itself. I mean, you just do nothing, and then you have an instance of P. Okay, so every problem is reducible to itself. We also have transitivity. So if P1 is polynomial time reducible to P2, and P2 is polynomial time reducible to P3, well, then P1 can be reduced to P3. You just go through an instance of P2 in between. Also, if I have two problems, for example, the partition and subset sum problems, that are mutually reducible, I can reduce one to the other, and I can reduce the second one back to the first one, what that's really telling us is that the two problems sort of have the same computational difficulty, give or take a polynomial number of operations. So it's not that they have identical computational difficulty, it's that their difficulties are the same up to a polynomial factor. And in particular, if we ever have mutual reducibility, what that's telling us is if you can find a polynomial time algorithm for either problem, you have a polynomial time algorithm for both problems. So for example, if you have a polynomial time algorithm for P2, you can then solve P1 in polynomial time by just converting it to an instance of P2, which you can do in polynomial time because it's polynomial time reducible. Okay, so we now know what a polynomial time reduction is. Here is a wall of text so that people don't send me angry emails. In your future computational complexity course, as I said a minute ago, you will see that there are actually multiple ways of defining reductions in general and polynomial time reductions in particular. And the different ways you can define these reductions have different rules. There are some types of reduction that are very strict and some types that are a little bit less strict. So in case you care, the one that we have defined here is something called a Karp reduction. And yes, that is our friend Karp of the Edmonds-Karp algorithm. And I should add that Edmonds is no stranger to computational complexity results either. In fact, one of the big results we're going to see, or big conjectures we're going to see later in this lecture, actually is considered to originate with Edmonds. So both Edmonds and Karp had a pretty diverse set of interests, I guess. So what I've defined here is called a Karp reduction and is considered to be one of the more strict forms of reduction. The main restrictions of Karp reductions are that the reduction must turn a single instance of P1 into a single instance of P2, and that it must map a true result to a true result. It can't invert the result. It can't say that if P2 comes back false, P1 is true and vice versa. That is considered a pretty strict requirement. So there are other forms of reduction, and we're going to touch on one of them in the next lecture. There are other forms of reduction where you're allowed to turn one instance of P1 into a whole bunch of different smaller instances of P2. That has its place, but there are cases where that can cause some confusion. So the types of reduction I'm working with here actually are pretty strict, and therefore you'll see do require a bit of extra legwork, but by being so strict, we can be assured that it's definitely going to produce a polynomial time algorithm if we get a polynomial time algorithm for P2. And the idea behind a Karp reduction is that what we're basically doing is saying, okay, I take an instance of P1, I then spend polynomial time converting it to an instance of P2. If later I can find some way of solving P2 in polynomial time, let's say it takes m to the d time or something, and we know that the size of the instance to P2 is equal to n here, so I create an instance of P2 of size n to the c. Really what I'm doing here is that means I can solve, if you give me an algorithm for P2 that takes m to the d time, that means I can solve P1 in this amount of time. And clearly, this is polynomial in n, because c and d in this case are constants. It could be a large number, but it is polynomial. Another thing, I'm going to come back to this in more detail later, but I'm just putting it here again so people don't send me angry letters. I keep talking about input size. I already alluded to this earlier. In a higher level setting, you would consider some nuances of input size, including things like how many bits do you use to encode things. When I say that the input is some set of size n, well, it's true that the size of the input is proportional to the number of elements of the set, but there are other factors in there. For example, how many bits do I use to represent each element of the set? To really oversimplify, we could sort of say, well, okay, I guess the number of bits you need could be something like log n or something. It could be some polynomial factor. And the key thing to understand here is that it might not always be log n, it could be something else. In a computational complexity course, you would want to consider that nuance, that there is going to be some extra contribution to the size based on how you represent the input stuff. Now, the reason why that's not a big deal to us is that when we think of input size, and again, I'll come back to this later, when we think about input size, we think about the total number of bits needed for the input, which means the bigger the input is, the easier it is to get a polynomial time algorithm. Because obviously, if n is really large, you have many more operations you can use before you end up taking too long. That means even if we fold in the number of bits into our measurement of input size, if our input contains a huge number of bits, that actually makes it easier to show that things take polynomial time. But in any event, it turns out that the transformations that we are doing in this lecture aren't really affected by the nuances you would need to worry about in a computational complexity course. What I'm doing here is just covering basically for the fact that I'm avoiding a bunch of extra difficulty in our results for the sake of proving what we care about, but that actually the results are still correct. The simplifications that I've introduced aren't going to break the results. They're just things that you don't need to consider in the context of polynomial time reductions. Now, we have shown that subset sum is polynomial time reducible to partition, and partition is polynomial time reducible to subset sum, which means if I can solve either of these problems in polynomial time, I can solve both of them in polynomial time. As we said a few minutes ago, what we're really showing is that the computational difficulty of both problems is similar, give or take a polynomial factor. Now, this by itself isn't very surprising. There are two reasons for that. One of them is that you already saw these reductions, both of them, 29 lectures ago in lecture 12. Okay, that's one reason. The other reason is that partition and subset sum do actually have some visible similarities. I mean, we framed them both as problems involving the antique scale. They both involve adding up a collection of integers to achieve a certain result. So maybe it's not too surprising that we can turn an instance of subset sum into an instance of partition and vice versa. But that was just the appetizer. So I'm saying that we're now concluding the appetizer course, even though it's now been about an hour and 10 minutes. It's going to be a multi-course meal, I'm afraid. So that was just the appetizer. It turns out I can construct, and so can you, polynomial time reductions between problems that seem to be really, really different. So let's do a couple of those. Here's one. Vertex cover. So that's a problem involving optimization of something over a graph. Vertex cover is polynomial time reducible to subset sum. These are two problems that are almost night and day, but they have some similarities that when you probe beneath the surface do become evident. This is what I meant earlier about hidden depths. A lot of these problems have quite a bit in common that isn't really obvious at a superficial level. Okay, so I'm going to go through a reduction of vertex cover to subset sum. So let's consider an instance of vertex cover. The input to vertex cover is a graph G and a bound K, because we're talking about the decision problem, and so because vertex cover normally is an optimization problem, to turn that into a decision problem, what I do is add a bound K, and the question becomes, is there a vertex cover of size at most K? Okay, so you give me an instance of vertex cover, G and a bound K. Our goal for the reduction is to find some way of creating a set S of integers, as well as a goal sum W, such that S has a subset with sum W if and only if G has a vertex cover of size at most K. Now, one simplification we can bring in right off the bat, which is really going to help us, is to observe that actually, if I can find vertex covers of an exact size, that actually is, in a sense, a more difficult problem than the version where it's size at most k. So if I find a vertex cover of size exactly k, well, clearly there is a vertex cover of size at most k. And I'm now pointing out that the opposite is also true, and I actually already explained why this was earlier when we were talking about the vertex cover problem. So for example, if I'm looking for a vertex cover of size 9, and I find a vertex cover of size 8, so we can see there's a vertex cover of size 8 shown here. If I want a vertex cover of size 9, I just take my vertex cover of size 8 and add an extra redundant extraneous vertex. So basically what I'm arguing here is that we can, in terms of our reduction, worry only about finding vertex covers of an exact size. We don't worry too much about the at most constraint. If there's a vertex cover of size 8, there will always be a vertex cover of size 9. So if I want a vertex cover of size at most 9, and the best I can do is find one of size 8, that's fine, because if there is one of size 8, there will be one of size 9. So I can refine our goal to save us a little bit of trouble later. Given a vertex cover instance gk, I want to create a set of integers and a goal sum such that S has a subset with sum w if and only if G has a vertex cover of size exactly k. So I have to find some way of turning this pair of graph G and bound K into a set S and a goal sum W. The reason why it was important that I did this exactly K thing is that one key difference between the two problems is that this at most K, in theory at least, allows multiple different sizes to be considered, whereas subset sum is done based on some exact value. I want a subset with sum exactly W, not less than or equal to W, but exactly W. So by translating the problem to say exactly, I can line up those two details between the two problems. And without loss of generality, that is a reasonable thing to do. Okay, so ultimately my reduction will result in me constructing a set S of integers. However, the integers themselves are if you look at the expression for how we construct them, it's not very easy to understand where they come from. So to build our way up to that, instead of initially talking about a set of integers, I'm going to talk, just to explain the reduction, I'm going to consider a variant of the subset sum problem where instead of adding a bunch of integers to achieve a goal sum integer, we're going to add a collection of vectors to achieve a goal sum vector. Okay, so consider some graph. Here's a graph, and now consider an incidence matrix for that graph. Okay, what is an incidence matrix? Incidence matrices are a standard graph theoretic thing. They are very relevant in some fields of graph theory, I guess. So I vaguely remember that on like the second day of my undergraduate graph theory course, an incidence matrix was defined, and I don't think I ever used it again until I first saw the reduction from vertex cover to subset sum. So make of that what you will. An incidence matrix is a matrix where every vertex has a row and every edge corresponds to a column. And if I look at the entry at row I and column j, that entry is set to 1 if the corresponding vertex and the corresponding edge are incident. So in this case, the edge QS does not touch vertex R, so this thing is set to a 0. On the other hand, the vertex RS does touch vertex R, so it's set to a 1. And similarly, let's say the vertex QS does touch vertex Q, so this thing is set to a 1. Okay, so the entries of an incidence matrix are either 0 or 1, based on whether the vertex that corresponds to a particular row is incident to the edge corresponding to a particular column. Okay, now as usual when I draw matrices like this, what I'm going to do is just draw the 1 entries only, so all the other blank entries are understood to be zeros, just to make it visually easier to see the ones. Before we go further, actually, before we consider vertex covers, observe that because of the way that edges work, I mean every edge has exactly 2 endpoints, notice that the sum of each of these columns is exactly 2. If I just add up the entire column of the matrix, every column must have sum 2. Okay, now let's consider some vertex cover of our graph. Okay, so here is a vertex cover, I've shaded it, QST. And we can shade the corresponding rows of the matrix blue as well. If I look at those rows and I add them all together, so I add together all of the shaded rows of the matrix and compute a sum, notice that the sum in every column has to be at least 1. because if I have a vertex cover, then at least one endpoint of every single edge must be in the vertex cover. So if I add together the corresponding rows, I should expect that a 1 is added in from the column corresponding to every edge, because every edge is covered. Conversely, if I go consider a set of vertices that isn't a vertex cover, so notice that the set QT isn't a vertex cover because the edge RS is missing. And if I go over to the matrix and I sum up the rows corresponding to my set of vertices, so this is the row Q and the row T, notice that RS sums to 0, the column RS, because RS is not covered. So we can actually use the sum of the rows as an indication of which edges are covered. Okay, so here's a condition. To select a vertex cover, choose a collection of rows in which every element of the sum is at least 1. Because if every element of the sum is at least 1, then every single edge is covered. And hopefully you can see where I'm going with this. I'm trying to turn a vertex cover into something that we can think of as being a sum. And I want to achieve a goal sum of some kind. The issue with condition 1, though, is that the goal sum is not a single value. It says every element of my sum is at least 1. So in this case, it's 1, 1, 2, 1, 1, 2. But there could be vertex covers where some entries are 2 and some entries are 1. There could be multiple vertex covers of this graph where the 1s and 2s might move around. Because all I care about is that every element of my sum row is at least equal to 1. In some cases, so if we look at, let's say, the edge QS, the reason the sum is 2 there is just because there are both endpoints of the edge QS happen to appear in the vertex cover. So I found a way of interpreting the vertex cover in terms of the sum of a subset of rows, but it's not an exact sum. It's just a lower bound. I want every entry of the sum to be at least 1, and we can observe it'll be at most 2, but it'll never be greater than 2, but it could be 1 or 2, and I could still have a valid vertex cover. So we're not quite there. We don't quite have a reduction because the subset sum problem requires an exact goal sum. And I mean also that the subset sum problem needs numbers, not vectors, but it turns out that step is not that difficult once we get there. Okay, so here's an observation. The maximum value of each entry of the sum has to be 2, because each edge has 2 endpoints, and therefore the sum of the entire column of the matrix corresponding to each edge is going to be 2. So here's an idea. What I could do basically, I guess I already mentioned this, but if I look at the cases where the sum is equal to 2, that's just the case where the corresponding edge is incident to 2 vertices in the vertex cover. So here's an idea. What I could do is observe that I know that the sum is going to be at most 2. Maybe I could find a way of making it so the sum is exactly 2 in all cases. And one way of doing that would be adding extra rows to the matrix that allow me to pad out the sum by at most 1 if I want to. In other words, if I can find a collection of rows such that the sum is at least 1 in every position, if I allow myself the option of adding 1 to some rows if I want to, or to some columns if I want to, that would give me a way of making sure that the sum in every position is exactly 2. I could add 1 to the cases where the sum is 2, but I could also choose not to do that. If I allow myself to pad the sum out by exactly 1, then I could get a situation where my sum is at least equal to 1, and I'm allowed to make it exactly equal to 2. Now, that's a lot of words, so I hope to explain that with diagrams in the next few slides such that you believe me. So what I'll do is I'll add 1 extra row to my matrix, so I no longer have an incidence matrix, because the incidence matrix is only this part. I'm adding extra rows to make this matrix something new. I add extra rows to the matrix with 1 row per edge. And I set the element of that row, so if I look at the row I add for edge PQ, I set the element of that row corresponding to the column for the same edge. I set that element to be 1. So there's PQ, the element for row QR, column QR, that's equal to 1. And of course, all of the other elements of that row are going to be equal to 0. So what this allows me to do, these extra rows, notice how it does allow me to pad out the sum in any column to up to 3 if I want to. If I then add up every single column of this, the sum will always come to 3. Now the trick here is if I choose a vertex cover, I can then add in a few of these extra rows to pad out the sum of that column, but only if I want to. If the column already sums to 2, I don't need to do that. But if the column sums to 1, I can do that. So we can think of these rows as slack rows. Now, the term slack rows it comes, I guess, from my optimization background in a sense. I like to think of them as slack rows because they're a way of sort of removing or picking up the slack. It allows me to ensure that the sum of every column is some exact number, and the slack rows are there if needed to pad out the sum. So for example, if I go back to the vertex cover I had before, QST, what I can do is add in a few of the slack rows. So if I look at, for example, the edge PQ, only one endpoint of the edge PQ is in the vertex cover, but I would like it if my sum could be guaranteed to always equal 2 all across the board when I have a valid vertex cover. So what I do is I just add in the corresponding slack row. Okay, and so then I can turn this into a new condition. With this new matrix, to select a vertex cover, choose a collection of rows in which every element of the sum is exactly 2. Now you might be wondering, wait a minute, by adding these slack rows, isn't there a way I could game the system? Isn't there a way I could use the slack rows to artificially make it look like I have a vertex cover when I don't? Now the key here is, if I bring in slack rows, the best I could do with slack rows is add 1. Which means if my sum has a 2 in every position, I must have at least one of the vertices that is the endpoint of the edge folded into that sum. So if the sum of a particular column equals 2, the slack row can't be doing all of that work. At least one of this sum has to come from an actual vertex. That's the key. Now that said, my hand-wavy explanation just there doesn't count as a proof. If you would like a proof, you're welcome to write one. Prove that any vertex cover can be represented by a collection of vertex rows plus 0 or more slack rows, such that in every position of the sum, I can see the number 2. Okay, that's one direction of the proof. The other direction is prove that if you find a collection of rows that adds up to all 2s, that you in fact have a vertex cover, if you only consider the rows that correspond to vertices. So you just ignore the slack rows that were chosen and consider only the rows that correspond to vertices. These two proofs are necessary to justify the reduction. Now the goal of this lecture is mostly to go through the existence of such reductions, so I'm not going to go through the proof myself. You will find that the proof isn't really that difficult. Okay, so condition number 2 now provides us between this correspondence between vertex covers and collections of rows such that the sum is equal to some exact value. It's going to be all 2s across the board. Now the problem with this is, if I go from some arbitrary collection of rows to a vertex cover, I've now lost control over the size. So previously, when I didn't have the slack rows, if I chose 3 rows and that was a vertex cover, I would have a vertex cover of size 3. But here I've chosen, 7 rows. And it happens that these 7 rows together correspond to a vertex cover of size 3, because the slack rows don't count as part of the vertex cover. They're just a convenience, a mathematical device so that the sum can be padded out. So if I look at my vertex cover QST, that happens to correspond to a collection of 7 rows, and then every entry of the sum is 2. If I look at this vertex cover that contains 4 things, that actually also corresponds to a collection of 7 rows. And the reason why I need fewer slack rows is that more of my edges have both of their endpoints covered. So there are fewer rows where I need to pick up the slack. Which rows need that? Well, actually, it's these 3 here. So the edge PQ is only covered by one endpoint, so I have to bring in the slack row for PQ. So is the edge QR and the edge QS. But these 3 edges are covered by both endpoints, and so therefore I don't need the slack rows for them. And so maybe you can see the problem here. I've got 2 collections of rows of size 7 that both correspond to vertex covers, but they're vertex covers of different sizes. And of course, the vertex cover problem that I'm solving depends on the size, and so I need some control over the size of the vertex cover I choose. There is not some obvious fixed relationship between the number of rows that I choose and the size of the underlying vertex cover. I need to add something else to this to get that control back. And then there's one more example. Here is a vertex cover of size 3 again, but this vertex cover happens to correspond to a collection of 8 rows of the matrix. And so here I have a vertex cover of size 4 that needs 7 rows. Here I have a vertex cover of size 3 that needs 8 rows. So clearly I need more control. Okay, so I want to find a collection of rows where every entry of the sum is equal to exactly 2, and where k of those rows are vertex rows. I need to make sure that the number of vertex rows I select is exactly equal to k to achieve what I want with my vertex cover problem. To do this, what I could do is add one extra column to distinguish the vertex rows from the other rows. Now, in the sources I've used, this extra column doesn't have a name, and I like making sure all the columns have names, so I took it upon myself to, I guess, assume the naming rights. And of course, that meant that I chose to call it column omega. So I had this new column called column omega, which obviously sounds really cool and mysterious. And the idea behind column omega is that I set it to 1 for every vertex row and 0 for every slack row. And observe that what this means is if I look at the sum of rows that corresponds to a vertex cover, every column except column omega will have a 2 in it, as we saw earlier. But the sum of column omega will just count the number of vertex rows that I chose, because I'm just adding in the ones from every selected vertex row. So what I want now is to find, to get a vertex cover of size k, I want to choose a collection of rows such that the sum of column omega is equal to the value k, the desired size, and the sum of every other column is equal to 2. Okay, so I've got that. I guess I should have called this thing, this is sort of condition 3. So this is the final version of our, the final condition that we need. I now have a way of using this sum of rows of this matrix as a way of finding vertex covers. Find some subset of the rows such that the sum has a k in the first position and 2's in every other position. Now, the question here is, how do I turn this into the subset sum problem? Because the subset sum problem doesn't involve rows of a matrix, it involves actual numbers. So how can we apply this to the normal subset sum problem? And as I said earlier, the reduction itself is just to create this set of integers. And when you see how to create the set, maybe you'll agree that it's sort of cryptic. So the question is, how can I go from the rows of the matrix to individual integer values? So here's one thing I can observe. For the sake of this observation, let's ignore column omega. Notice that the maximum sum in any column under any circumstances, even if I choose way too many rows, the maximum sum of any column is exactly 3. There is no way I could ever add any collection of rows together such that the sum of any particular column is greater than 3. It could be 3 if I select way too many rows, but it will never be 4 or 5 or anything greater than that. And the reason for that, of course, is because you have a 1 in the 2 positions corresponding to the vertices at the endpoints of the edge, plus an extra 1 corresponding to the slack row. Okay, so the maximum value of all of these positions, the lower order positions in the sense of that sum row, the maximum value of all of these is 3. Now, the maximum value of column omega is different because the maximum value of column omega, I guess, if I were to choose every single vertex as part of my vertex cover, the sum of column omega could be as much as the size of the vertex set. So, of course, what I just discussed only applies to the columns that aren't column omega. Here's an idea. Let's just ignore column omega again for the sake of argument here. I could view the elements of each row, not just the sum itself, but also the individual rows of the matrix, as the digits of a number in base 4. Now the trick here, like why are we using base 4? The trick here is if I think about the way a number in base 4 works, the digits I'm allowed to use in base 4, every base 4 number can have, each digit will either be 0, 1, 2, or 3. And I realize that because of what we just saw, which is that each of these positions of the sum can be at most 3, and certainly no position of the matrix will ever be greater than 1, that means that if I'm adding together a bunch of rows of the matrix, I will never actually have an overflow between columns if I treat them as numbers in base 4. So for example, if I look at the row for vertex R, I just add back the zeros, that corresponds to this number in base 4, 1, 0, 1, 0, 1, 1, 0. Since the maximum sum of every column except omega is 3, if I add together the base 4 representations of a bunch of rows, I will not have to do a carry operation. There will be no overflow in any of these columns because the maximum sum of the column is 3, which is a valid digit in base 4. Now that said, of course, if I add a bunch of rows together, I could produce a number greater than or equal to 4 in position omega. But if I view this as being the most significant digit, then if an overflow happens in this column, it'll happen in this direction. It'll go over to the left, and therefore it won't affect the sum in the other positions. And so it's true that yes, this wouldn't really work formally as a digit in base 4, but I could view this would actually just be, this would overflow into this number in base 4. If an overflow happens in column omega, therefore, it just sort of overflows to the left. It doesn't touch any of the things happening to the digits to the right. And actually that turns out to be good enough. So I actually have enough if I treat each row of the matrix as the digits of a number in base 4. I can actually turn the rows of the matrix into individual numbers and turn this into an instance of the subset sum problem that we know and love. Okay, so let's actually walk through that. Now, this is almost basically here for completeness, because once you see the expansions, you'll see it is pretty cryptic. Let GK be an instance of the vertex cover decision problem, and suppose that the vertices and edges are numbered like this, just for the sake of convenience. I'm going to define this value Dij, and you can think of this as just sort of being one entry of the incidence matrix. So Dij is 1 if Vi is incident to Ej, and 0 otherwise. Then, for every vertex, I'm going to define this value AI, and it's going to be this number in base 4. And so there's column omega, and then here are the columns corresponding to each of the edges of the graph. Now, if I actually write that out, if I think of what that means in base 4, it turns out to be this thing here. So, of course, any number in any base can be written out as a sum, as a combination of coefficients multiplied by powers of the base. So it ends up being, here is the sort of orthodox base 4 expansion of this, or I could write it like this, because the variable Dij is just 1 or 0. Really what I'm saying is add in the power of 4 if there is a 1 in that position, and that just means if Vi is incident to that edge. Okay, so that's AI. So AI is the base 4 encoding of one row of the matrix, and then to encode one of the vertex rows, the row for vertex Vi. If I want to encode the slack rows, let's just define a value B, which has a 1 in the position corresponding to the edge I'm talking about. So for edge EJ, I want to have a 1 in position J. Okay, so we'll just add a 1 there. That would be 4. That means that the value B is just 4 to the J. All right, and so then I create my set S, which will just be the rows of the matrix, or in this case, the base 4 encoding of the rows of the matrix. They're the vertex rows, they're the slack rows. And my goal sum is just the case where every single digit is 2, if I sum up the columns corresponding to edges, and the sum of column omega is just 4 to the m, or it's actually, this is a typo, sorry, it should be k times 4 to the m. Because what I want is, in position m, in a broad sense, I want there to be the value k. The number of vertices that I've chosen, if I add up column omega, needs to equal the value k. I'm going to write that in a bit more neatly. There we go. Now, it's true that I think about position m of the base 4 number is supposed to correspond to column omega, but what if an overflow occurs? What if the value of k is greater than 4? It turns out that that's no big deal, because as I mentioned earlier, the overflow just means that there are going to be that there are going to be more base 4 digits than I need, but the extra digits are going to be off to the left. They're not going to affect this sum here. And you could write a proof of that if you wanted to, but mercifully we don't have to write that proof in this course because this is not a computational complexity course. We're mostly using this as a way of building to our ultimate punchline for this lecture, which is the fact that if a polynomial time algorithm exists for subset sum, we can definitely solve vertex cover as well. And this is enough to complete the reduction. So I've turned an instance of vertex cover into a set S and a goal sum W, such that if there is a subset of S with sum W, then there is a vertex cover of G with size K, which in turn means that there is a vertex cover of G with size at most K, which means I've solved the vertex cover problem. And therefore, vertex cover is polynomial time reducible to subset sum, and that means that if I can solve subset sum in polynomial time, which of course I don't know whether that's possible, but if I could, then I can solve vertex cover in polynomial time as well. So there's one pretty involved reduction between two very different problems. And here's another one. 3 satisfiability, which involves Boolean formulas, can be reduced to vertex cover. This is also sort of weird. I've got Boolean formulas on the one hand, and of course this is just find me an assignment of truth values such that the formula is true. That's the question. And over here I've got this sort of optimization flavored problem involving graphs. And yet, if I can solve vertex cover in polynomial time, I'm claiming that that means I can solve 3 satisfiability in polynomial time. And it's another one of these involved reductions. All right, so 3 satisfiability, it involves formulas in 3CNF. Now, it's been a while, so let me remind you what 3CNF is. 3CNF would be a collection of clauses with exactly 3 literals joined together by the logical AND operation. And remember that a clause consists of literals joined together only by the logical OR operation. Okay, so consider some 3CNF formula with some number of clauses and some number of variables. We'll call the number of variables n and the number of clauses m. In this case, they're both 3. 3 clauses, 3 variables. It turns out we can take a 3CNF formula on n variables and m clauses and turn it into a graph on 2n plus 3m vertices. So in other words, I'm going to add 2 vertices per variable plus 3 vertices per clause. And I can demonstrate that the graph I produce has a vertex cover of this size if and only if there is a satisfying assignment to the formula. This is a pretty weird one. Okay, so here's how we construct the graph. Now, the graph I'm going to construct corresponds to this formula here, which has 3 clauses over 3 variables, x1, x2, x3. Step 1. I'm going to create for each variable a pair of vertices joined by an edge. So I'm going to call these things variable vertex pairs. I suspect at least once I'm going to get my words jumbled up and say vertex variable pair. So I beg you to indulge me when I do that. Okay, so I create 3 pairs of vertices and each one contains a variable and its negation. So it contains x1, not x1, joined by an edge, x2, not x2, joined by an edge, x3, not x3, joined by an edge. Notice that if I have n variables, then what I've just done is I've created 2n vertices. Okay, so there's where the 2n vertices came from. And these are the variable vertex pairs. Okay, so now what I'm going to do is, for each clause, I'm going to create a triangle of vertices. So we're going to have 3 clauses, and therefore I'm going to draw in 3 triangles. Now I'm going to color them in like this just so that it's clear that these each correspond to one separate clause. So I'm going to call these things clause triangles. So for each clause, I add a clause triangle. Now formally, you can't just say triangle usually, so let's say copy of K3, the complete graph on 3 vertices, which is a triangle. So for each clause, create a clause triangle and label the vertices in the triangle with the literals in the clause. So if we look at this clause here, it maps to that clause triangle. So there's x1, there's not x2, and there's x3. And similarly, if I look at this clause here, there's not x1, there's x2, there's not x3. So I label the vertices of each clause triangle with the literals of the clause. I can do this in any order I want. The order I've chosen here literally is actually just so that the layout looks a little bit less impossible to understand when we get there. Okay, so the next step is I'm going to join together the vertices inside each clause triangle with the matching vertex in the variable vertex pair. So I'm going to join this x1 to that x1. There's x1. Here's not x1. So I join the not x1 in the third clause to the not x1 in the variable vertex pair. I'll join up, so this x2 goes here, this x3 goes here, this goes there, x2 goes down here, and you can see this is going to be a bit of a mess. There's this x2, and then there's this x3. So I just join up each vertex in the clause triangle with the corresponding literal in the variable vertex pair. I end up with this. This looks only a little bit better than what I just drew by hand. Now, I claim that a minimum vertex cover of the resulting graph actually does correspond to a satisfying assignment. Now, I'm going to build up to that. So let's take a look at a minimum vertex cover. So the blue vertices shown here correspond to a minimum vertex cover of the graph that I just produced. Notice, and this is sort of by design, we can prove this separately. Notice that the vertex cover contains exactly 2 vertices from each clause triangle and exactly 1 vertex from each vertex variable pair. Actually, we can go further and observe that any vertex cover, minimum or not, no matter which one you choose, every vertex cover must have that property. You need at least 2 vertices from each of the clause triangles and at least 1 vertex from each vertex variable pair or variable vertex pair for the vertex cover to make any sense. Because there are 3 edges internally in each triangle and you need to cover all of them. So how are you going to do that unless you choose at least 2 of the vertices from the triangle? Similarly, to cover the edge between the variable and its inverse, you do have to choose either x1 or not x1. So here is a minimum vertex cover. One other related thing, this is actually basically what I just said, because you need at least 2 vertices from each triangle and at least 1 vertex from each variable vertex pair, that means it's impossible for any vertex cover to exist that contains fewer than this number of vertices, n plus 2m. So 1 vertex per vertex variable pair, 2 vertices per clause. Okay, so here's my claim. If the graph G that I produced from this construction from a particular formula Z with n variables and m clauses has a vertex cover of this size, and so recall from the thing in the previous slide, this is as small as a vertex cover can ever get. No graph produced by this construction could ever have a vertex cover smaller than this. My claim is that if there is a vertex cover of that size, then there is a satisfying assignment of formula Z. Okay, so how do I illustrate this? Basically, I'll just do a sketch of the proof here. If I have a vertex cover of size n plus 2m, well, obviously, because I need to have this n must correspond to choosing 1 vertex from each variable vertex pair. That means exactly 2 vertices in each clause triangle must be in the cover. There can't be 3 because if one clause has 3 vertices, some other clause must only have 1. So there must be exactly 2 vertices from each clause triangle must be in C. What that means, therefore, is that there must be exactly 1 vertex from each triangle that isn't in my cover. So let's just highlight those. I'll call these the orange vertices. These are the vertices in the clause triangles that are not in the vertex cover. And there must be exactly 1 of these if I have a vertex cover of this size. There must be exactly 1 of these per clause. Since each of the orange vertices is not in the vertex cover, and because, of course, every orange vertex is connected to one of the variable vertices, the edge that connects them must be covered by the variable vertex. The orange vertex isn't in the cover, and so the edge connecting it to the variable vertex must be covered by its other endpoint. Okay, so I'm just make a note of that. So these are the 3... I'll wait for the slides to catch up to us. Also, notice that if I take the orange vertices and I set each of them to true, so I say x, in this case, I've only chosen x2 and x3, x2 equals true, x3 equals true. Notice that if I do that, obviously each of the clauses is going to be satisfied because the orange vertices, there is 1 orange vertex per clause. If I ensure that all orange vertices evaluate to true, every clause will evaluate to true because the clauses themselves are logical OR operations. So the first clause, for example, is this. As long as at least 1 of these 3 literals is true, the clause will be true. So if I set x3 to be true, the whole clause ends up being true. So therefore, I can construct a satisfying assignment by just setting each variable to true if the variable vertex for that xi is in C, and false if the variable vertex for the corresponding inverse variable is in C. And that actually is equivalent to what I was constructing on the previous slide. So here I said set all of the orange vertices to true. But actually, if you think about it, because the orange vertex isn't in the cover, the thing at the other end of the edge connecting it to a variable vertex must be in the cover instead. And because I connected these vertices I connected together x2 and x2, or in general, I connect each literal to the corresponding literal in the variable vertex pair, setting each of these to true is actually just the same thing as choosing the vertices in the vertex cover that are part of the variable vertex pair and setting those to true. So in other words, I can make a satisfying assignment, in this case by setting x1 to be false, because the literal not x1 is covered in the variable vertex pair, x2 to be true, because the literal x2 is in the vertex cover, and x3 to be true. And you can go and verify that indeed that does satisfy all 3 clauses of the formula. Okay, and that is a valid satisfying assignment. Okay, so a couple of exercises. Here is the graph produced by a 3CNF formula that has 4 clauses. See if you can work out what it is. And here's a minimum vertex cover of that graph. It has size n plus 2m, which means, according to our construction, that there must be a satisfying assignment to the formula. And so figure out what satisfying assignment it is. So using the rules that I just described, so that would be the one described on this slide here, work out the satisfying assignment corresponding to this particular minimum vertex cover. Remember that there could be more than one minimum vertex cover, and in fact, there could be more than one satisfying assignment. So work out the one corresponding to this particular vertex cover. I'm actually not done the reduction because I have to prove an if and only if. It isn't sufficient to say that if there is a vertex cover, there must be a satisfying assignment. I sort of have to show the converse as well. So here it is. If I have a 3CNF formula that has n variables and m clauses, and I produce the graph by the construction we just described, and the formula has a satisfying assignment, then the graph will have a vertex cover of this size, of size n plus 2m. Okay, so right off the bat, this formula has 4 clauses and 3 variables, x1, x2, x3. And it happens that this assignment, x1 equals false, x2 equals false, and x3 equals true, is actually a satisfying assignment of that formula. Okay, so this formula has a satisfying assignment. I'm going to show how we can use it to construct a vertex cover of size n plus 2m. Now, of course, this is not a proof by example or anything. What I'm doing is sketching out the way that we construct these things if I wanted to write a formal proof. Okay, so step 1. So I take my satisfying assignment, so just to remember what that is x1 is false, x2 is false, and x3 is true. So false, false, true. So I create my graph construction, and then I add the literal corresponding to the truth value of each variable out of the variable vertex pair. I add that to my vertex cover. And we notice that because there are n variables doing this, so again, this corresponds to the assignment x1 equals false, x2 equals false, and x3 equals true. Doing this will add exactly n vertices to my vertex cover, 1 for each variable. Because of course, I would never add both x1 and not x1, because x1 is either true or false and never going to be both. Okay, so step 2. I now go and look at the clause triangles, and I find any vertex, we'll go back to step 1 for the sake of the illustration. Let's take a look at this clause triangle here. Notice that, and this is actually by design, I mean this is a function of the thing we saw earlier where the satisfying assignment comes out of the vertex cover, but notice that this vertex here in the clause is adjacent to something in the cover, but these two vertices down here are not. So this vertex x2 is not in the vertex cover. This vertex not x3 is also not in the vertex cover. So step 2 is take all of the vertices in clause triangles that are not adjacent to something in the cover and add them. So I do that. So these two vertices are not adjacent to things that I added in step 1. These two vertices are not adjacent to things I added in step 1. And this vertex is not adjacent to something that I added in step 1. Now notice that as of the end of step 2, I haven't added 2 vertices per clause. And the reason for that is because the rules that I used didn't require me to do that. And that's no big deal. It turns out that step 3 is just pad out the vertex cover to ensure that all edges are covered. So actually, as of the end of step 2, this clause triangle is all good. It is fully covered. And so is this one. It has 2 vertices in the cover, and so it's fully covered. However, this clause triangle has a problem because it doesn't have 2 vertices in the cover, and we saw earlier that it needs to have that. And moreover, like, you know, who's covering this edge here? And finally, this clause triangle is in real trouble because it contains no vertices that are in the cover, and therefore none of its 3 edges are covered. And so step 3 is just add as many vertices as you need to ensure that each clause has exactly 2 vertices in the cover. Now, I hope I explained that properly, but basically the idea is you can do whatever you want here. All you want to do is make sure that when you're done step 3, that every clause triangle has 2 vertices in the cover. So I could, for example, say, let's add that one, and for this clause, I could add these 2 here. That's all I care about. It could be any 2 vertices from each clause. All right, and when I'm done, I have the n vertices corresponding to variables, and I have 2 vertices per clause, and so the total size of my vertex cover is n plus 2m. So if a satisfying assignment exists, and we could write a formal proof that this construction actually always works, if a satisfying assignment exists, there is a vertex cover of size n plus 2m. Okay. Now, the thing I really want to show off is, hey, what happens if the formula isn't satisfiable? Like, it would be great to see how the reduction also still works properly if I give you a formula that isn't satisfiable, how that means that there isn't a vertex cover of the right size. The problem with this, it turns out, is that if I want a 3CNF formula that isn't satisfiable, I needed to have 8 clauses or more. And that's a bit of a rough one because, you know, with 4 clauses, it's already an incredible mess. So unfortunately, I won't be able to do that. I won't be able to illustrate what happens if you have an unsatisfiable formula. What I can do by way of apology is at least show off what would happen if I try and construct a vertex cover of a satisfiable formula for a particular non-satisfying assignment. So I could at least show that off. I could at least show off sort of what would happen if you had a formula that was not satisfiable. So here's a formula that we already know is satisfiable. We saw a satisfying assignment of it earlier. But consider this assignment. x1 is true, x2 is true, and x3 is true. It turns out that this is not a satisfying assignment. And the short answer for why that is look at this clause here. This clause requires at least one of x1, 2, and 3 to be false, and they're all true. So this assignment is not a satisfying assignment. Let's see what happens if we try to construct a vertex cover using our technique with this non-satisfying assignment. Okay, so after step 1, I add the vertex corresponding to each true literal out of the variable vertex pair. So this vertex, and this vertex gets added. After step 2, I have to go through and add in step 2, what I do is I add every vertex from a clause triangle that is not adjacent to something I've already chosen. So for that, I would have to add not x1 because it's not adjacent to something already chosen. I'd have to add not x2, but I wouldn't add x3 because you can see that the edge connecting this, it is actually adjacent to something I've already chosen. Okay, out of the second clause, I would again add not x1. I would not add x2 because it's adjacent to something that I already chose, and I would add not x3. Notice that everything seems to be working so far. I've chosen 2 vertices per clause triangle. Okay, for this clause here, I don't add this vertex, but I do add this one, and I do add this one. And again, everything seems to be working out. Okay, but here is the clause triangle corresponding to that clause that we're going to have a problem with. So this clause is not satisfied by our assignment. Our assignment where x1, 2, and 3 are all true will not satisfy this clause. So what happens? So in step 2, I have to add every vertex that is not adjacent to something I've already chosen. Okay, so I have to add not x1 because this hasn't been chosen. I have to add not x2 because this hasn't been chosen. And I have to add not x3 because this hasn't been chosen. Okay, so after step 2, the vertex cover contains all of these vertices here. So and notice that I chose 3 vertices from the last clause to add to the cover. Now, I will admit that I made a mistake when I was illustrating step 2 for some of the other clauses. Just bear with me. So here, I added 3 vertices from this clause, and we're going to see this has to break something. The size of vertex cover we want is this size here, n plus 2m. That is, I choose 1 vertex from each vertex variable pair and exactly 2 vertices from each clause. I know that I need at least 2 vertices from each clause. So if any clause ends up with 3 vertices, I will not get a vertex cover of the desired size. And so basically what we've just illustrated is if you have a non-satisfying assignment, at least one of your clause triangles will require 3 vertices. And that means that you will never get a vertex cover small enough to meet the criteria. And so if we had a formula where there was no satisfying assignment, then every single vertex cover would have at least one clause triangle with 3 vertices in it, and that would mean that there would be no vertex cover of this size, and that would mean that the reduction still holds, that both of the claims from earlier still hold up. Okay, so more exercises. Construct the graph corresponding to this 3CNF formula, and then construct the vertex cover that goes along with this particular satisfying assignment. There's something to try. Okay, so what have we shown? Well, we showed that we can reduce 3 satisfiability to vertex cover, and that we can reduce vertex cover to subset sum, and that we can reduce subset sum to partition. We also actually showed that we could reduce partition back to subset sum. What this is telling us is, if I can find a polynomial time algorithm for partition, then I can solve subset sum, vertex cover, and 3 satisfiability in polynomial time. Okay, great. So that implies some connection. It also is sort of interesting because, frankly, of all the problems on the list, I've always had a soft spot for partition. I've always felt that partition seemed like a rather easy problem. It's very interesting to see that, in fact, partition is at least as difficult as all of these other problems. But it goes further. It actually turns out that every single problem on this list is polynomial time reducible to every other problem on the list. And my goal in showing you the reductions from vertex cover to subset sum and 3 satisfiability to vertex cover was to give a sort of taste of how complicated these reductions can be, but how they do work, how we actually can reduce one problem to another, even though it looks sort of bizarre to do that. And it turns out that we could produce reductions between any pair of these problems. Some of the reductions would be incredibly hideous, but they would exist. We could create them. And that means if I can solve any of these problems in polynomial time, then at least theoretically I can solve all of the other ones as well. One thing I should observe right now while we're on the subject, though, is that just because there's a polynomial time reduction doesn't mean that if I had an algorithm it would be fast. So if I have a reduction from P1 to P2, where the running time is like n to the 100, well, yeah, okay, so if I have a polynomial time algorithm for P2 that would let me solve P1 in polynomial time, it wouldn't take, it would be pretty onerous. It would take a very long time. We're talking about this theoretical notion of polynomial time. There is at some point going to have to come into play, I guess, a sense of practicality, a sense of how long am I willing to spend waiting. The thing we have to keep in mind, though, is that n to the 100 ultimately, for large enough values of n, is still way better than, let's say, 2 to the n. Any polynomial, even a really ridiculous one, is still better than an exponential function. Okay, so before we go any further and talk about this idea that I can reduce any of these problems to any of the other problems, I actually want to explore more about what these problems have in common. And so to do that, why don't we take the problems that we know about, so both the ones that can be solved clearly in polynomial time and the ones, maybe that can't, and group them together into what are called complexity classes. So we can take a set of computational problems and group them according to some aspect of the complexity of solving them. And so we call these things complexity classes. One very natural complexity class is to take all problems that can be solved in at most polynomial time, even problems that can be solved in constant time and logarithmic time count, because they can be solved in polynomial time or less. Let's take all of them and put them in one class. We'll call it P. The class P contains all problems that can be solved in polynomial time. Okay, now here's some more technical stuff. You feel free to skip over this. This, again, is to avoid some angry emails. Now, usually we define computational complexity classes. That is, the formal definition of the class P is usually given in much more complicated terms than this. The definitions I'm giving here actually are correct, but we use more complicated ones in a computational complexity course to allow us to compare them to each other, basically, to allow very crisp definitions, because it turns out there are tons of complexity classes, tons of them, way more than I'm going to discuss here. Another thing we have to understand, and we're actually going to touch on this a bit next time in the next lecture, is that there's also a question of what operations cost, what operations add to the total running time of a problem and what operations don't. This comes down to which model of computation that we're using. The model we've been using all the way since lecture 1 and that we are going to continue using is the random access model. And recall that the characteristics of the random access model are that you can access any memory location in constant time, and also that we've been assuming that addition and subtraction and multiplication and things like that are constant time as well. Now, reasonably, adding two numbers, if I say compute a plus b, that does require work. And depending on how big those numbers are, it could take a different amount of work. And so if we are being really careful, we might also want to consider how much work it takes to perform addition or if statements or whatever. However, for the sake of polynomial time work, we don't need to worry about that. So even if we considered the amount of time each addition took, so if I had an algorithm that took, I don't know, n to the 5th time on our random access model, even if I considered it under a model where each memory access doesn't take constant time, so it actually takes time to crawl all the way through memory to find each memory location, and each addition or subtraction or whatever took some other input-dependent amount of time, all that would really do is add a polynomial factor. It would multiply the running time by some polynomial factor. So instead of n to the 5th, it would be, n to the 100 or n to the 10th or something like that. And that means if all I'm talking about is polynomial versus not polynomial, I actually can continue to use the random access model. So if you're in a computational complexity course now, and for some reason watching this video for old time's sake, please remember that I'm aware of this limitation, and we shouldn't use the random access model for analysis of stuff like algorithms that run in logarithmic space or logarithmic time or whatever, unless we're really, really careful about everything. But the random access model is just fine if we're talking simply about the difference between polynomial and not polynomial. So it is possible to discuss polynomial time and slower, so exponential time or whatever, using the random access model, because all of the overhead that might be disguised by the random access model, so memory access time or the time it takes to do addition or subtraction, will actually require polynomial time or less. So it doesn't hurt anything. We're not talking specifically about, n to the 5th versus n to the 6th. If we were, some of this overhead might be significant. We're just talking about n to some constant versus n to some other constant. We don't mind that much if we have to pad the constants by a bit to account for overhead. Okay, well, thank you for listening to this announcement. Great, okay, so what is the complexity class P? Okay, a decision problem D is in the complexity class P if there's an algorithm that can solve some input instance of D, in worst case, polynomial time in S, where S is the size of the input. Now formally, and I will actually adopt this formalism here, even though we could get around it, I think. Formally, when we talk about the size of the input, let's assume that the size S refers to the length in bits of a binary encoding of the input. So if I say the input is a graph, well, really, when we talk about the size of the input, the size is going to be the size of some representation of the graph encoded in binary. So for example, I could represent the graph by an adjacency list and then represent that adjacency list as an array encoded in binary, or an adjacency matrix or something. And so that doesn't make much of a difference to us because we know that the size of the representation of a graph is polynomial in the size of the graph. We actually know that from, what was that, like lecture 23 or something like that? We know that the way of representing all of the inputs that we know and love, sets of integers, lists, graphs, and things, if we represent it in binary, the size in bits of that representation is polynomial in the size of the thing at a high level. So if I take a set of integers with the size of the set equal n, if I represent this in binary, the size of the binary representation is some polynomial of n, which means, again, all we really care about with this definition is that there is what we know to be a polynomial time algorithm to solve the problem. Okay, so let's take a look at a decision problem. Here it is. Here's min-cost path. Our definition of P, as you saw in the previous slide, so it talks about decision problems. A decision problem D is in the complexity class P. There are generally considered to be sort of separate complexity classes for problems like counting problems and optimization problems. I won't get into that here, so we're going to adopt a very simple definition of the class P that applies only to decision problems. So our definition of P only applies to decision problems. So if I want to talk about the complexity of optimization problems with respect to the class P, I have to first frame them as decision problems. So here is our familiar min-cost path problem, but it's been reframed as an optimization, as a decision problem. If I think about demonstrating that min-cost path is in P, what I have to show is that there exists an algorithm that has polynomial running time in terms of the size of the input as far as a binary representation is concerned. Okay, so an input consists of a graph, there's the graph, as well as 3 extra things. And we can assume these are numbers, so u, v, and k. we can characterize this input size in terms of the number of values as, well, okay, the number of, it's proportional to the size of the graph, so v plus e plus 3, I guess, if I represent the graph as an adjacency list. If I take an adjacency list and then I encode it in binary, that will add some extra factor, but it'll be a constant factor, or at worst, a polynomial factor. I suppose there are cases where it might be non-constant, not relevant to our course. Please don't write me angry letters. Therefore, it is reasonable, because we know that the size of the input is proportional to v plus e if we use an adjacency list, and we know that the Bellman-Ford algorithm has a running time that is polynomial in this expression, that it is possible to solve the min-cost path problem in polynomial time. And so here's the slide saying some of the same disclaimers I just said for the last 5 minutes. Okay, and so since we can find the true minimum cost of a UV path in polynomial time, polynomial with respect to this number, for example, using the Bellman-Ford algorithm, because I can find the true minimum cost, obviously I can solve the decision problem in polynomial time as well. Okay, so this is my roundabout way of concluding that this problem, min-cost path, is in P. So by framing each of these things as a decision problem in a similar manner, we can show that all of them are in P. Each of these is a polynomial time problem in the complexity class P. Now we can turn these problems into decision problems as well. This set of problems that we've been struggling with for this entire lecture that don't seem to require polynomial time as far as we know. We can write them as decision problems, but they are not known to be in P. I can't tell you that they're not in P, because there could be a polynomial time algorithm for them. But we don't know that they're in P. But they have something in common. So although we can't say they have polynomial time algorithms, we actually can observe there is something convenient about them that they all have in common that isn't true of some other problems. Okay, so if I look at the subset sum problem, an instance of that would be a set S and a goal sum W. The total size, so this lowercase s I've been working with, is proportional to the size of this, which is just size of S all plus 1, which is n plus 1. We know of this algorithm to solve subset sum in this amount of time, but that's not polynomial in terms of the input size, because W can be any value. W is not proportional to the input size. And so all of the known algorithms for solving subset sum are actually exponential in the worst case. We've seen a couple, we've written a couple ourselves, but nobody's found a polynomial time algorithm in terms of the input size. The problem with this is that just because all of the known algorithms are exponential doesn't mean that all algorithms are. Maybe somebody one day will find a polynomial time algorithm for subset sum. Or for all we know, maybe they'll find a polynomial time algorithm for partition. That would be sufficient because we know that subset sum is polynomial time reducible to partition. If we could prove that every algorithm for subset sum was exponential, so if I could write a proof that it's impossible to create an algorithm for subset sum that is polynomial time, that every algorithm must require exponential time, that of course would imply that subset sum is not in P. It also implies that any problem that can be polynomial time, that can be reduced to subset sum in polynomial time is not in P. Because if subset sum is not in P, then any problem, actually this is written the wrong way around. Any problem where subs that can be reduced in polynomial, that's true. Any problem that subset sum can be reduced to in polynomial time is in P. So what I mean to say is this. Or actually, no, the next slide, I'm getting ahead of myself. Before I get to that, the question then is, okay, wait a minute. So what I've just observed is, and I'll unpack, this wording is very, now that I read it this way, it's sort of confusing. We'll ignore that wording for now. If I could prove that every algorithm for subset sum was exponential in the worst case, that would tell me that subset sum is not in P. But then the question is, okay, so we can't do that. I've just said already a few times in this lecture that there is no known polynomial time algorithm, but we haven't proven that one doesn't exist. So we're not ready to say something like this yet. But a natural next question is, are there any problems where that is the case? Are there any problems that we have proven must require exponential time, where there is no polynomial time algorithm? And the answer is yes. It's something that we haven't studied, but maybe you've heard of it. So checkers is a two-player board game. Now normally we play checkers on an 8x8 board. If you don't know how to play checkers, then why not pause the video and go learn? It's a pretty simple game. It's pretty easy to find a site that will let you play it online and practice a little bit. It's easy to learn, and I think if you know a bit of it, it becomes easier to appreciate what I'm about to say. Now, one caveat, so in some variants of checkers, including I think some sets of official rules for it, there are specialized rules that I guess you could call them anti-frustration features, which say that if the game goes on for some protracted period of time with nothing interesting happening, so an example would be, I think a popular version of this rule is, if no pieces have been captured for 40 moves, then the game is automatically considered to be a draw. So the game immediately ends if the two players have spent 40 moves doing basically nothing useful. So just sort of wasting time, I guess. That's an anti-frustration rule because people stop wanting to play the game if it takes 40 moves and nothing happens. For the sake of this discussion, let's assume that no such rules are in effect. It actually turns out that algorithms solving the game have a much easier time if this rule is in place. So assume that no such rules are in effect. The game keeps going until it reaches an actual end. It doesn't end arbitrarily because we've reached a point where no human player would want to continue. So here's a task. I give you a checkerboard in some particular state. So the game has been played for some number of moves, and I say, here's the board. Is it possible for the red player to force a win? Now, this is a term of art, force a win. So what does that mean? The idea of forcing a win means, is there a way for red to play such that at every single step, no matter what move the other player just made, there is some move that red can make such that eventually red is guaranteed to win. So starting from this board, is there some way that red could play that no matter how well the other player played, no matter what they knew or what they did, red would win in all cases? That's what's called forcing a win. And I hope you agree that although that's a bit of a complicated definition, that it is well defined. Is there a way to take from this board for red to play such that they are guaranteed to win, no matter what the other player does? Now, whether red can force a win, we could figure this out using a recursive backtracking algorithm. We could basically try every possible move for red, and then for each move for red, we try every possible move for black, and then for each of those, and we just go back and forth and work out whether there's a pathway such that no matter which moves are made by the other player, red can always win. That would be what I call a backtracking algorithm. Often in this context, it's called something like branch and bound. You might hear reference to something called alpha-beta pruning as an example of a type of branch and bound technique. Now, there's a weird issue here, which is that with a fixed board size, like 8 by 8, the number of possible states of the board is actually a constant. I mean, it's a really large number, but we can compute it. It's just some constant value, which means we have this annoying special case of, well, technically that means if I wanted to enumerate all possible states, that would take constant time. It would take a very long time, but it would technically be constant time. Okay, fine, let me fix that problem. Let's talk about generalized checkers. Generalized checkers is played on an m by n board. And the idea is by parameterizing the size of the board, that means that the size of the input is now not going to be guaranteed to always be the same. It's not always going to be 8 by 8. Okay, so given the particular state of an m by n checkerboard, determine if it's possible for red to force a win. Now, I haven't talked about what the rules of generalized checkers are, but for the purposes of this discussion, that's not very important. It's pretty easy to generalize the basic checkers game to an arbitrary size of board. It turns out that on an arbitrary n by n input board, deciding whether red can force a win, deciding that, answering that yes or no question, requires exponential time. Not just that there is an algorithm out there that solves it in exponential time. No, I'm saying that it requires exponential time. There exist proofs that it is impossible to solve this problem, this decision problem, faster than exponential time. Now, a related problem that I think is a bit more accessible, but not a decision problem, is given a particular state of the board, figure out what the best move for red to make is. Or alternatively, to make that a decision problem, here is a state of the board. Consider, I don't know, like this move here. Is this the best move for red to make? This has also been proven to require exponential time. Here is a paper. Here is an early result of the fact that generalized checkers requires exponential time. There are no algorithms to solve the problem of deciding whether a particular player can force a win better than exponential time. And I will add, this is the first time we have seen a problem that provably requires exponential time to produce a yes or no answer. There are tons of problems that we've encountered in passing over the past 40 lectures that will require exponential time. So an example of an easy problem that requires exponential time is, I'm going to give you some set S where the size of S equals n, and I want you to list every subset of S. But the problem is the number of subsets of S is 2 to the n. In order to produce 2 to the n things, it's going to take 2 to the n time. That's obviously going to require exponential time. You can't list all the subsets of something in polynomial time. That obviously requires exponential time, but that's not the same issue as we've encountered here. What we're talking about here is a decision problem. Here's a checkerboard. Can red force a win or not? Yes or no? This is a yes or no question that has been proven to not be solvable in less than exponential time. So there are algorithmic problems out there that we can prove require exponential time to solve. I guess a question to think about is a problem like subset sum harder or easier than solving the game of checkers? To me, it seems like having to consider whether red can force a win under any circumstance requires a huge amount of work and is a lot more complicated than deciding whether there's a way for me to balance a scale using a subset of provided weights. To me, it does feel like subset sum is an easier problem. And I want to illustrate one reason why I think that. One other thing to think about before we stop talking about checkers is, suppose it were possible. Suppose we could solve that decision problem, and I told you, yes, it is possible for red to force a win. Or, for example, I tell you, this is the best move for red to make at this point. What would I have to provide if you wanted proof of that? So if I told you this is the best move, or yes, it's possible for red to force a win, what would I have to give you for you to believe me? What would you need for me to convince you of that? So just think about that. Okay, so I want to talk about why subset sum and the other problems on our list from earlier, these things have something in common. There is some hidden depth that they share, but also there's something about them that does make them feel a little bit easier than these exponential time problems like the game of checkers. So while it seems to be difficult to actually find a subset B, if you give me a subset B that adds to W, it's very easy for me to believe you. That is, if you tell me that there is a subset that meets my criteria, and you show me the subset B, it's very easy for me to verify that you are correct. So it's easy for you to give a compact piece of evidence that lets me verify your conclusion. So for example, suppose I give you the subset sum instance where S is equal to this set here and W is equal to 197. And you come back and say, yeah, the decision problem evaluates to true, but I don't buy it. I say, prove it. Well, you could just provide me this subset. Notice how the subset B that you provide me is pretty compact. It is of a polynomial size with respect to S, obviously, and it's really easy for me to take that subset and, in polynomial time, verify that it is in fact a subset that adds to W. So subset sum is a problem where, although it's very difficult to find a solution, if you can come up with one, it's very easy for somebody else to look at it and independently verify that the solution qualifies. And all of these problems have the same property. While finding a solution, seems to be difficult, for all these problems there is a very compact and easy to verify, and by easy I mean in polynomial time, there is an easy to verify representation of a solution. So although finding it is difficult, if you find one, I can easily check your work in polynomial time. So in the case of subset sum, if I have this input with this goal sum, if you provide me this subset, this is what we call a certificate of the outcome, a certificate that the problem evaluates to true. Now you're going to notice that when I talk about certificates, I only talk about them in the case where the answer is yes. I'm not going to talk about what it means to be a certificate if the answer is no. That's not relevant to this discussion, although in a complexity course there is a different discussion you will have, a very similar discussion that you will have that has to do with certificates of the case where the answer is no. Okay, so in general, a certificate is an extra piece of information that some independent verifier can use to easily verify that a decision problem has a particular yes or no, or a particular result if the result is yes. Now, this is the thing I said a minute ago. Notice that a single subset B can serve as a certificate for a true result, but giving you one subset wouldn't be a way to prove a false result. A false result is a result that applies to all subsets. So if I say that there is no subset, to prove that to you, I'm making a statement about every possibility. To prove that there is a subset, I only have to show you one subset with that property. There could be many that have that property, but I only have to show you one of them. Okay, so I want to do something a bit more formally with respect to certificates. So consider an input SW to the subset sum problem. And suppose that you provide me with a set B as a certificate that the result is true for this input. I want to justify formally that I can verify the certificate to demonstrate that your answer actually is true in polynomial time. Here's how I would do this. If I'm independently verifying your work, I should check everything, because maybe you've given me a completely erroneous subset B. So for example, if I say, is there a subset of this 1, 2, 3, 4 with W equal to 1000? And maybe you hand me this certificate here. Let's do 500, oh, I don't want to do 500, 600 and 400. This subset does add up to 1000, but of course this is not a valid certificate because it's not a subset of the set that I started with. So when I verify the certificate, I'm going to be as suspicious as I can. I'm going to check every single thing about it. Okay. So you have told me that there is a subset that adds to W, and you have given me a set B as a certificate. So the first thing I'm going to check is that actually a subset of S? Because if not, it is not a certificate. Once I know it's a subset of S, then I'm going to check that it adds up to equal W. If both of those conditions hold, then the certificate is valid, and subset sum does indeed evaluate to true. Now, while it might be difficult to find the certificate B, to find a valid subset, this verification can easily be done in polynomial time. I mean, this is what, like n or n squared time, probably. And similarly, for the partition problem, if you give me a set S of n positive integers and the partition problem evaluates to true, well, one certificate I could provide you so you could check my work is just giving you a partition. I could say, here are the sets L and R, and you have to now verify that this certificate is valid. And again, you want to be as suspicious as you can, because I might try and pull a fast one and give you two sets that appear to be a valid partition, but they're a partition of something else. Okay, so let S be an input to partition, and suppose that somebody gives you this pair LR as a certificate. Here is how you might verify that. The first thing you do is check that L union R adds up to S. In other words, that every single weight appears in either L or R. Then you check that the intersection of L and R is nothing, because that way no weight is appearing on both sides of the scale. And then finally you verify that the stuff on the left adds up to the same thing that the stuff on the right adds up to. And again, finding the partition appears to be difficult, but if I give you a partition, this certificate can be verified very easily in polynomial time. Okay, what about max cost path? Now, the max cost path decision problem is, I give you a graph, I give you two endpoints, and I give you a bound, and I ask you, is there a path from U to V with cost at least K? Well, an obvious certificate of that would just be to provide the path. So if you hand me a path, I could easily verify that the cost of that path is greater than or equal to the bound K. Now, of course, there is more to it, because verifying this is just the tip of the iceberg. Okay, so here is the input to the max cost path problem, and suppose that somebody hands me a certificate that looks like this, a path in the form of a list of vertices. To verify that, I want to check everything. So I do want to check that the cost of the path is at least is greater than or equal to K, but first I'm going to check that we actually have a path, because otherwise I don't care what its cost is. So how do I know that I have a path? Okay, well first, every vertex along the path has to be an actual vertex of the graph. Okay, that's condition number one. Second, if I look at two vertices that are next to each other on the path, they have to be connected by an edge. In this case, it has to be a directed edge if it's a directed graph, so from P1 to P2, for example. So verify that this thing here is in the graph as an edge for every pair of adjacent vertices along the path. Then I have to verify that no vertex appears twice along the path, because it wouldn't be a path in that case. And finally, I verify that the first vertex is the starting vertex I wanted, and the last vertex is the destination vertex that I wanted. Only once I verified all of that stuff do I bother checking that the cost of the path is what I was expecting. And although this is a little bit tedious, certainly I can do this verification in polynomial time. So finding a path might be difficult, but if you find me one, I can use that as a certificate to check your work very easily. What about vertex cover? Well, in the case of the vertex cover problem, the vertex cover itself would be a valid certificate. How would I check that? Okay, so let GK be an input to vertex cover, and suppose that you hand me a particular set C and tell me that the result is true based on the certificate C. Here is how I would verify that. First thing I would do is I would verify that the set C actually is a subset of the vertex set. And then I would verify that if I pick any edge of the graph, that one or both of the endpoints of that edge is in the cover. And that means by the time I'm done these two conditions, that means we actually have a vertex cover. And then I would verify that the size of the vertex cover you provided is at most equal to the bound in the problem. And so in cases where the decision problem evaluates to true, so the decision problem version of any of these things, each of them does admit a compact certificate that can be verified in polynomial time. And actually the word compact is a sort of weasel word there. Really what I mean is a certificate of polynomial size, so something that I could feasibly verify in polynomial time. And we can actually give a name to problems that have this property. So if a problem is a decision problem that can be verified in polynomial time, then we're going to add it to a class called NP. So we defined earlier the class P to be problems that could be fully solved in polynomial time. We have these problems here that we don't know if they're solvable in polynomial time, but we do know that we can conveniently verify them in polynomial time. We'll call that the class NP. Okay, so the definition we'll use for that is, let D be a decision problem, and consider some input Q where D evaluates to true. And again, notice I'm only worrying about cases where it evaluates to true. We're not going to worry about the case where it evaluates to false or how to wrangle that. That's a separate issue. It turns out it's all tangled up in this issue, but in a way that goes far beyond the scope of this course. The problem D is in the class NP if there exists an algorithm that takes Q and some certificate C provided from outside. So who knows how we got the certificate? That could be difficult. But there's an algorithm out there that takes Q and a certificate and verifies in polynomial time that D evaluates to true. In other words, it's able to take the original input and a certificate and conclusively verify that the answer is true based on the contents of the certificate. Now, notice that the verification, so I said that the input Q has size S, and the verification has to take polynomial time in S. That's a requirement. And so because the verification is expected to take polynomial time in the original input size S, that means that the certificate itself has to have polynomial size. If a certificate had exponential size, you wouldn't be able to even read the certificate, the whole thing, in polynomial time. So the definition actually requires that the certificate itself also has polynomial size in terms of the original input size. That's a big deal. There are lots of ways we can verify certificates. There are lots of problems that are outside of NP that might even require exponential time in all cases that have certificates. But verifying the certificate could take more than polynomial time. So a problem is only in NP if there is a way to verify a certificate for a true result in polynomial time in terms of the original input. Now, where do we get this name NP? Well, it's something that we can't really explain in this course. We'd like to say, oh, NP stands for not polynomial. No, we don't know that. NP could be. For all we know, all the problems in NP could be doable in polynomial time. NP actually stands for non-deterministic polynomial time. I don't really have a way of contextualizing the meaning of the word non-deterministic. The best that I can do is say that the word non-deterministic relates to the idea that to be in NP, a problem just has to have some way of verifying a certificate in polynomial time. Notice that the definition doesn't explain where the certificate comes from. You don't need to be able to actually compute the certificate in polynomial time, just verify it. The word non-deterministic can be interpreted sort of to mean that assuming that you create a certificate by guessing it randomly, you're just really good at guessing certificates, then you can verify it in polynomial time. And so you can think of the idea of non-determinism here as being related to the fact that NP doesn't depend on how the certificate is created. It could be created via any means, via some non-deterministic process, just that we can verify a certificate, a valid certificate, easily. So by describing certificates and verification procedures that took polynomial time, we have actually shown that this max cost path, vertex cover, subset sum, and partition are in NP. The way that you can prove that a problem is part of NP is showing that there is a way of verifying a certificate for that problem in polynomial time. Let's try proving that the dominating set problem is in NP. All I have to do here is to show that there is a way of verifying a certificate in polynomial time. So I have to show that whenever the problem evaluates to true, there exists a certificate of the solution that we can verify in polynomial time. Okay, well, I guess the obvious certificate that we could use is the dominating set itself. So if the problem evaluates to true, there must be a dominating set S with size at most k. That's the statement of the problem. So S itself could be a certificate, and we know that the size of S is less than or equal to the size of the vertex set. So obviously the size of the certificate is polynomial in the input size. And here is a verification procedure. Suppose you tell me that the answer is true for a particular graph, and you give me a set S. Okay, so first I verify that S is a set of vertices. Then I verify that for every vertex in the graph, either that vertex is in the set, or that vertex has a neighbor. Oh, whoops, that should say vertex U. That vertex has a neighbor that's in the set. And then I check that the size of the set is at most k. And clearly this can be done in polynomial time in the size of the graph. And so I've just shown that dominating set is in NP. It is a problem that is in NP. Some exercises to try out. I think you'll find these are quite easy to do. Prove that the 3 coloring problem is in NP. So find some certificate and show that it can be verified in polynomial time. Prove that 3 satisfiability is in NP. So find a certificate and prove that that can be verified in polynomial time. Okay, a natural question that comes up here, and I remember having this question myself when I finally got to a theory of computing course where P and NP were defined, and I had been wondering all along, what is this whole P and NP business? And we finally got to NP, and it was defined in terms of verifying things. And I was like, wait a minute, what's the big deal here? Like, why do we care so much about problems based on the complexity of verifying them? Isn't the whole point of studying problems like subset sum and partition because we want to solve them? I want to actually find a subset. I don't care how long it takes to verify a subset. I care how long it takes to find a subset. So why do we care about this class NP if it's based on how long it takes to verify something? So it's a bit of a nuanced answer. The real reason that we care about it is because it gives us an umbrella for all of these problems that we know seem to be rather similar. So it's true that the reason we care about these problems is because we want to solve them fully. We want to compute a solution. We don't really just care about these problems because we want to verify solutions. Our goal is to find solutions, find vertex covers, find partitions, whatever. It's true. And so the question then is, we haven't been able to find polynomial time algorithms for these problems for some reason. No polynomial time algorithms are known. So a natural question is, well, what do we know about them? Like, why are these problems so difficult? Finding something that these problems have in common is a way of, I guess, putting them all under one roof, at least understanding sort of where their complexity lies, even if all we know about them is the complexity of verification. So the fact that we've shown that for all of these problems we can verify a solution easily is actually important information. It shows us that the difficulty is apparently related to finding the solution, not understanding whether something is a solution or not. I know that sort of seems like a pretty fine-grained point, but I think if you meditate on that for a bit, maybe you can appreciate that that is pretty profound. The fact that I can show you a vertex cover, and it's very easy for you to know that you're looking at a vertex cover, that's a big deal. If instead I told you that red is able to force a win in checkers, here is some incredibly long explanation of why that is. The solution itself, maybe the solution might have been easy to find, but what's so difficult is understanding that it's a solution. So the fact that we've shown that these problems can be verified easily is actually telling us something meaningful about their difficulty. It's telling us that the difficulty amounts to a sort of searching related issue, finding a solution. Once we have a solution, it's very easy to understand that it solves the problem. And so if I demonstrate that a problem is in NP, that is a way of showing that the problem has an easy to understand solution which may or may not be easily found. Actually, to say cannot is getting ahead of myself. So there are lots of problems that are in NP where the solution actually can be easily found for reasons that are going to become clear in about like 2 slides. Okay, so just to recap, the class P contains all decision problems where I can actually find a solution in polynomial time. The class NP contains all decision problems where some solution somebody else has already found can be verified in polynomial time. Okay, so a claim. And this claim, of course, sort of refutes some of the wording that I've used here. So let's say may not be easily found, because the result I'm about to describe sort of contradicts the word cannot there. So my claim is every problem in P, every problem where I can find a solution easily, is also part of NP. In other words, what I'm saying is that P is a subset of NP. In my opinion, looking at these two definitions, it's sort of clear why that has to be the case. So P is the set of problems where I can find a solution easily. And NP is a set of problems where I can verify a solution easily. Now, it seems to me that if I can just find a solution in polynomial time, verifying a solution is going to be very easy. And so it shouldn't be too surprising that P is a subset of NP. Okay, but I will write a proof of that anyway. Okay, so let's let D be some problem in P. Okay, so the fact that D is in P means that it's possible to compute a solution to D in polynomial time. Now, since D, so now let's demonstrate that the problem D is in NP. So to do that, I have to show that if D evaluates to true, there is an easily verifiable certificate that can be verified in polynomial time. So suppose that D evaluates to true on some input. Now, since D can be fully evaluated in polynomial time, I don't really need a certificate at all. I could just verify the true result by recomputing the entire answer from scratch, because I can do that in polynomial time. So therefore, I can verify a true result in polynomial time using an empty or non-existent certificate by just rerunning the computation for D. Okay, there's my proof. Now, do you think that you were sort of shortchanged with that? Do you feel like that's a bit of a cop-out? Oh, I could just rerun the algorithm. I didn't actually provide a verification procedure at all. Okay, fair enough. I have an alternative proof. If you want to be really pedantic about it, let's try this. So you give me a polynomial time algorithm to solve D. We know that one exists because D is in P. Okay. So here is a certificate I could create. As a certificate, what we do is we run the algorithm to solve the instance of the problem. So you give me some input, and I run the algorithm to solve the problem in polynomial time. And I just make a list of every operation performed by that algorithm. So you give me an algorithm that can provably solve the problem in polynomial time. I run the algorithm, and I make a transcript of every single operation that algorithm does. Now, because the algorithm performs a polynomial number of operations, because it runs in polynomial time, the transcript that I make, the list of operations, would have polynomial size. If I want to verify that transcript, verify the certificate, all I do is I walk through the list and just verify that each operation performed matches the algorithm that you were using. I would argue that that is a way of verifying that the answer was correct, because if the algorithm was proven to work correctly and I verify that every operation was performed as it was supposed to be, that is a way of me verifying that the answer is true. And I think that is a non-trivial certificate. So there are two ways of justifying that P is a subset of NP. But as I said, I think it's fairly intuitive that if I can fully solve a problem in polynomial time, unsurprisingly, I can also verify the answer in polynomial time. And so what do we know about P and NP? Well, we know that P is a set of problems that is a subset of the set NP. There are, however, some problems here where we don't quite know whether partition is outside of P but in NP, or, frankly, whether partition is actually in P. We actually have no way of knowing either way. Well, at the moment. I mean, maybe one day somebody proves this. As of right now, in August 2025, there is no proof that partition is in P, nor is there a proof that partition is outside of P. So we don't know anything about the relationship of the problems on our list from earlier with respect to P. So we know that P is a subset of NP. Are there any problems here? Are there any problems that are in NP but not in P? Now, of course, if that were the case, that would mean that P and NP aren't the same. If there's at least one problem that's out here, that means that P is not equal to NP. So do we know that? Well, unsurprisingly, no, we don't. There are no proofs out there that P is not equal to NP. If I were able to prove that there is no polynomial time algorithm for the partition problem, that would be sufficient to prove that P is not equal to NP, because that would prove that partition, which we know to be in NP, is not in P. But we haven't been able to prove that. Okay, how about this? We don't know of any problems that are not in P but are in NP. So all the problems that we know about that are in NP may or may not be in P. So does that mean that P equals NP? Is it true that everything in NP can be solved in polynomial time? Well, we don't know that either. There are no proofs out there as of August 2025 that P equals NP. If P equals NP, then any problem that could be verified in polynomial time could be fully solved in polynomial time. That is a pretty provocative statement. The idea that the ability to verify a problem efficiently implies that you can solve the problem efficiently as well. But we don't know. We haven't been able to prove that P isn't equal to NP, and we haven't been able to prove that P is equal to NP. All we really know is that P is a subset of NP, and it turns out there are tons of other complexity classes as well. We also know, for example, that NP is a subset of this class, exp. The class exp is the class of all problems solvable in exponential time. Obviously, P and NP are subsets of exp because if I can solve it in polynomial time, I can obviously solve it in exponential time. If I can verify a certificate in polynomial time, I could just iterate over all possible certificates, which takes exponential time, and try all of them, which means actually any problem in NP can definitely be solved in exponential time. And we've demonstrated that for a couple of problems. We know, for example, that subset sum and partition can be solved in exponential time. We also, I don't think it's hard to believe that finding a minimum vertex cover can be done in exponential time as well. Just iterate over every vertex cover possible. Iterate over every subset of vertices, check the ones, find any that are vertex covers, and then choose the smallest one, and you've got a minimum vertex cover. So all we really know about these three complexity classes with respect to each other is that P is contained in NP. It might be everything. It might not. NP is contained in exp. We actually don't know very much about whether NP, the relationship between NP and exp, besides that NP is a subset of exp. Whether or not it's a proper subset is some other question. Okay, and so one last point. I want to finally demonstrate what I said earlier, which is that if we find a polynomial time algorithm to any of the problems on our list, then we can solve all of them in polynomial time. And to talk about that, I want to go back to the satisfiability problems. Okay, so the circuit satisfiability problem, which is where you give me a digital logic circuit and I tell you whether or not it is possible to ever make the output true, that is in NP. And the reason is because if I give you a satisfying assignment as a certificate, I can evaluate the circuit by just looking at the output of each gate in polynomial time. And unsurprisingly, if you give me a Boolean formula, I can use a satisfying assignment for that as a certificate and just evaluate the formula. And I guess it shouldn't surprise you that if I hand you a Boolean formula, so here's a Boolean formula that is an arbitrary satisfiability instance. So if I hand you this Boolean formula here, and I give you some satisfying assignment, you could just plug it in and evaluate the formula. That would be one way of validating the certificate. And so satisfiability is also in NP. And it shouldn't surprise us that if I restrict satisfiability to CNF formulas or to 3 CNF formulas, that is also in NP. Incidentally, 2 satisfiability is also in NP. 2 satisfiability is actually in P, but that's fine because we know everything in P is in NP as well. So 2 satisfiability is in NP. Here's an interesting observation. So a computer's processor and memory are built out of digital logic gates, or at least they can be. Yours is, mine is, but I suppose we could leave the door open to there being computers out there that do deterministic computation like the ones that we know and love that aren't built out of logic gates, although we'll touch on that a bit in the next lecture, in fact. But it's certainly true that these days a computer's processor and, in fact, its memory are built out of digital logic gates like these. So wait a minute, if I run a computer program on a computer processor, and the computer processor is built out of logic gates, isn't it true that I could just build a circuit to hard code any computer program? And the answer, as it turns out, is yes. It's really weird to think about that, but the answer is yes. And this has some really bizarre implications, so it leads to a bunch of dominoes falling. And the idea is basically, what that's telling me is that if I can turn any program into a circuit, then I could turn a program that runs in polynomial time into a circuit of polynomial size. In other words, I could add a few gates for each operation, basically a constant number of gates corresponding to each operation, more or less. There's a whole bunch of other complexity there, but that's my high-level summary. And what that's sort of telling me is basically that if I have any decision problem in NP, I could take the verification verification algorithm for that problem and turn it into a circuit. And that leads us to something called the Cook-Levin theorem. Now, a few lectures ago, when we talked about the max flow min cut theorem, I said that the max flow min cut theorem, in my opinion, is the most profound theorem of this course. And that is true. I stand by that. In a future course, for example, a computational complexity course or maybe a theory of computing course, you will see the Cook-Levin theorem in its full glory, and it will be, if not the most important, at least the second most important theorem of that course. It's not the most important theorem of this course, really, because we're using it, I guess, on loan from a computational complexity course. The Cook-Levin theorem isn't actually a single statement, so it's an amalgamation of a bunch of other theoretical results. This means if you look up the Cook-Levin theorem in a book or on Wikipedia, you're going to get slightly different definitions. I've tried to write a definition that's pretty magnanimous. And so this is a general purpose definition of the Cook-Levin theorem. The Cook-Levin theorem says if D is some decision problem that is known to be an NP, then D is always going to be polynomial time reducible to circuit satisfiability, or to regular satisfiability, or to CNF satisfiability, or even to 3 satisfiability. In other words, these 4 problems are catch-all problems that every single thing in NP can be reduced to in polynomial time. And the biggest implication of that is that if we were to find a polynomial time algorithm for even one of these, then every single thing in NP could be done in polynomial time. As I said a minute ago, again, the term Cook-Levin theorem refers to a broad swath of different results. It's sort of an aggregation of different things. So if you see it written in a book or something, it might say something like just this statement here, just the one about circuit satisfiability, but I have seen books that state it in terms of these 2 at the bottom. I've seen books that state it only in terms of formula satisfiability. It's no big deal for reasons that'll become clear in a few minutes. But basically, actually, even the way it's stated here sort of implies this. Because everything in NP is reducible to each of these 4 things, that also means that all 4 of them are reducible to each other. So actually, stating it in terms of all 4 of them is a little bit redundant, because if I know that everything is reducible to circuit satisfiability, then so is regular satisfiability and 3 satisfiability. And so the basic idea behind the proof, and the proof is a bit of a thing, so we're definitely not going to do the proof here. You've got to save something for your future computational complexity course. But basically the idea is, if I consider a problem D, which is in NP, then there must exist a polynomial time verification algorithm for D. If I then take an input to my problem D and I represent it in binary, which we know we can do, so the input to any algorithm arguably can be represented in binary because we implement algorithms on a computer that uses binary. So if I take the input to my verification algorithm and I represent that in binary, the verification algorithm itself can be transformed into a Boolean circuit whose inputs are the binary values of the input to the problem. And the way I transform the verification algorithm into a circuit is basically by hard coding the operations of the algorithm using digital logic gates. And the circuit evaluates to true if the string is a valid encoding of an input where D would evaluate to true. So I can turn the verification algorithm into a verification circuit. And then the question becomes, is there a satisfying assignment of the verification circuit? Because the Boolean circuit evaluates to true if the input is an input where the decision problem D would evaluate to true. And so what that's telling us is that because I can turn the validation algorithm for any problem in NP into a circuit, then if I can find a polynomial time algorithm for any of these, because it turns out we can actually also turn it into a circuit which is in 3CNF or a circuit that is in CNF, if I can find a polynomial time algorithm for any of these, then I can solve any problem in NP in polynomial time. And the term we use for problems like that is that these 4 problems are NP-complete. They can be used to solve any problem in NP. And so if we find a polynomial time algorithm for any NP-complete problem, that means that P is equal to NP. That means everything in NP can be solved in polynomial time. Okay, so formally, a decision problem D is called NP-complete if D is in NP and every other problem in NP can be reduced to D in polynomial time. Which means if I discover a polynomial time solution for any NP-complete problem, every problem in NP can be solved in polynomial time. The Cook-Levin theorem is notable because it gave us the first of these results. It was able to sort of provide us the bootstrap to prove that other problems are NP-complete. The Cook-Levin theorem showed us that those 4 satisfiability problems are NP-complete, but we can now use polynomial time reductions to show that other problems are NP-complete as well. And as of now, there are thousands, if not tens of thousands of NP-complete problems that are known. There are books you can get that are just lists of NP-complete problems. That is how many of them there are. And so if a polynomial time algorithm is found for any of the various thousands of NP-complete problems out there, that means that P equals NP. On the other hand, if P is not equal to NP, then no polynomial time algorithm can exist for any NP-complete problem. And as I said, there are thousands of these. That would be a huge result either way. It actually turns out that all of the problems on our list from earlier are NP-complete. If I can find a polynomial time algorithm for any of them, even the lowly partition problem, then everything in NP can be done in polynomial time, and that would mean that P equals NP. If I wanted to prove that a particular problem is NP-complete, here are 2 different ways I could do that. Probably the way you'd use is strategy number 1. So first, show that the problem is in NP. Now, if something is, we won't talk about the case where the problem isn't in NP and still everything in NP can be reduced to it. That's a separate thing called NP hard. So if I want to prove something is NP-complete, prove that the problem is in NP, find some other NP-complete problem, and show that I can use my problem D to solve that problem. So if every problem in NP can be solved with D prime, which is NP-complete, and I can solve D prime with D, well, that of course means I can solve everything in NP using problem D. Alternatively, I could find some NP-complete problem D prime and just use 2 reductions to demonstrate mutual reducibility. That would be sufficient to show that D is in NP. Although, as we saw earlier, proving that a problem is in NP isn't so difficult, so why not just do that? Okay, so vertex cover is NP-complete. I'm stating this as a theorem now, but it actually relies on stuff that we talked about like an hour ago. So we proved earlier that vertex cover is in NP. It's very easy to verify that a particular set is a vertex cover of a particular size. We also showed earlier that you can reduce 3 satisfiability to vertex cover in polynomial time. That means, because 3 satisfiability is NP-complete by the Cook-Levin theorem, that means any problem in NP can be solved via 3 satisfiability. And that means that because I can solve 3 satisfiability with vertex cover is NP-complete as well. Subset sum is also NP-complete. We proved that subset sum was in NP. It's very easy to verify a certificate. We also showed that vertex cover can be reduced to subset sum. Since we now know that vertex cover is NP-complete, that proves that subset sum is NP-complete as well. Partition is NP-complete. And that's because we earlier reduced, in polynomial time, partition to subset sum, and also, frankly, subset sum to partition, and this is the direction that we care about. So we know that subset sum is NP-complete, and we can use partition to solve subset sum, which means that partition is NP-complete as well. And so it's actually currently unknown whether there are any problems that are in NP which are not in P and also not NP-complete. Currently, all we really know about are a bunch of problems that are in P and a bunch of problems that we can prove are NP-complete, and a few that are sort of uncertain, but we can't prove at the moment that there are any problems that are not NP-complete but also not in P. There is one, though, that's a candidate. So here's a decision problem about graph isomorphism. I give you 2 graphs, and I ask you, yes or no, is one isomorphic to the other? Nobody's been able to prove that this problem is in P, and also nobody's been able to prove that this problem is NP-complete. If somebody were able to find a proof that this problem is somewhere between being in P and being NP-complete, that would of course be sufficient to prove that P is not equal to NP. And there are those that suspect that this problem has that status. This problem seems a little bit too easy to be NP-complete, but it seems like it might be a little bit too hard to be polynomial. But actually, we don't know. So here's an example of a candidate for a problem that's not as hard as the hardest problems in NP, like these ones. The NP-complete problems are the hardest problems in NP. But graph isomorphism also doesn't seem yet to be easy enough that it's solvable in polynomial time. Although, frankly, we don't know that these aren't solvable in polynomial time either. So one extra little aspect of that mystery is related to this, whether there's any problems in the middle that aren't polynomial but also aren't NP-complete. Lots of fun stuff for when you take a theory of computing or computational complexity course. And we're about ready to wind down this algorithms course. But you know, there was something that came up earlier where I guess we sort of have to discuss it, which is I showed this diagram of this hierarchy of complexity classes. We've got the polynomial time problems, the ones that we know we can solve in polynomial time. We've got the class NP of problems that can be verified in polynomial time, but we don't quite know what's going on with the relationship between P and NP. Is P equal to NP? Is P not equal to NP? Well, we don't know anything about that. That's a computational complexity question beyond the scope of this course. We also know that there's this class exp of problems that can be solved in exponential time. And we know, for example, that checkers is in exp. We don't necessarily know much else about the relationship between the problems in exp and the problems in NP, for example. We know, of course, that if a problem is solvable in polynomial time, that it's easier than problems that require exponential time. But wait a minute. I said there were tons of other complexity classes, and I've drawn this diagram of set inclusions, and my eye is immediately drawn to the outside. We spent this lecture talking about apparently hard problems. And I just talked about how there's problems solvable in exponential time, but is that as hard as it gets? If we're going to talk about hard problems, how hard can we go?